years ago, when 4 projects were awarded by the Commission in the same call, the LCBAT 10 call. So basically, we have the same starting point. And now almost towards the end, you can see then later during the coffee break, some demonstrators, some posters, where we highlight the individual outcomes, which are then, of course, different. So a quick look on the agenda. So first of all, in the first session, the first block, we will have general overviews, just 3, 4, 5 minutes per project, just to give you an idea what is Marble, Helios, Liberty, Albatros, and a new member, IBATman, I come to this later, about. Then we go into the details. The second session is about the battery system, more on the system macro level, solutions, innovations, and we highlight different stories from the 4 projects. The second session goes more into the details on the battery pack innovation for high performance. We have also 4 presentations here. And then then a coffee break, of course, so just to refresh and have the chance to chat with us and have a look on the demonstrators. And then the last session is on the detail, on the brain, the BMS, the battery management system. So that's the idea for our workshop today. As I said, COLLABAT started like 4 years ago with 4 projects, and we are in the middle right side of the value chain. So we're not into materials, anodes, cathodes, chemistries. We are producing, prototyping battery packs, and we're integrating the battery pack into the vehicle for the first use. But of course, on the right side, we're going towards the second life and of course the recycling issues, LCA, of course. But that just to make sure where we are. It's pretty obvious. We're all talking about the uptake of electric vehicles, e-mobility. And one of the shortage and the downsides is that the battery packs were too heavy. And the range was not enough for most of the customer, at least for the customer experience. So we need to increase the energy density, and we need to speed up the charging time or shorten the charging time. All 4 projects started with challenging objectives. So we need to reduce the battery compared to the benchmark, which was a Tesla 3 car model, by 20%. We need to extend the battery lifetime up to 300,000 kilometers in first life. We need to improve the life cycle assessment, and we have to also deal with knowledge innovations on sensors and thermal management. All 4 founder projects look pretty much the same with some slight differences. So Helios, for example, we have a modular concept and a mixed chemistry. We will use 2 different modules in the same pack. We will come to the presentation later. Marble is on the same way, focusing on weight reduction, charging time reduction, LCO, of course. But then also specifically on the easier disassembly and the repairability. Albatros is also, as all the projects, also keen on further weight reduction, shorter recharging time, and LCA improvement. And they will validate their pack based on a BMW i3 vehicle. Whereas Liberty's demo platform will be a Mercedes EQC, I think, in 2 weeks in Stuttgart. Next week in Stuttgart, okay. Edo can tell you more. This is the final event where they will be at Mercedes. And all 4 projects are about to finish, more or less end of this year, early next year, maybe mid next year with the extension we are requesting. But COLLABAT will not stop. So there's life afterwards. And we are very glad that we have 2 new project members, IBATman and InnoBMS, which are mainly focused on a BMS story. And these projects have recently started. So they will continue the idea of a cluster with discussions and joint dissemination projects. And of course, further projects, researchers, institutions are highly welcome to join us with their ideas, as long as there's a project behind, which is then part of the European Commission's funding schemes. Beside dissemination, what we're doing today here, and then also with the stand at the Battery Innovation Days, one of the major, I think, highlight of the COLLABAT cluster are these subclusters. These are expert groups, so closed-door discussions, not public discussions, between the different projects on different topics. So one was on sustainability LCA, the second one was on testing validation, and the third one was on BMS. And there, the project experts, technical experts, many of them are here today, were sitting together virtually, of course, or sometimes meeting if there was a coincidence, and then discussing specific technical issues without going into, of course, confidentiality issues, but in a very productive way to look for synergies and also problem solver ideas, etc. And from there, so we developed a couple of webinars, and we also thinking maybe at the very end to publish 1 or 2 white papers. So to go public with this knowledge transfer, knowledge sharing. And this is something we hope that the new 2 project members will also continue to work on this exchange among peers, among experts. And finally, here you feel free to contact individual projects. Here are the contact addresses from the coordinators and the communication dissemination managers. Thank you so far. And then I'll invite Eduard Piqueras from Marble project to give us a first introduction. Thank you.
Okay, I was very a cappella. Okay, and then yes, and apart from working on pre-award on Horizon Europe, I coordinate Marvel project, and today I want to say that it's an honor to me to be back here. I was graduated on industrial engineering in the University of Catalonia in this school, so it's very nice coming here back to explain our work here. And I want to say also, I think we are really lucky to be here, all despite we don't have the complete room. But I think we are all very, very, very lucky. We will hear all the innovations we had in the 4 projects, and I think it's going to be a very nice afternoon here. So well, let's proceed with the presentation of Marvel. I will introduce you the project, and I don't know exactly how we pass. It's here, great. And let's go. Let's go quick, because the importance today is that you meet our technical experts and they explain you what the innovations are. But just to introduce our project, well, as Thomas said, this is a history of 4 years ago. We got together this group of titans from battery field, some research centers. You see Eurecat, IREC, the University of Ingolstadt, working with companies, working with specific components for the battery, Smart Cell Manager, Junction Box, you see here Ficosa, ASA, Zagrati, and then manufacturer of batteries, ABL, and also with other relevant partners in automotive. Okay, we get together for mainly going to the 3 main goals. No, we want to tackle those points that prevents the end user of electric vehicles to buy an electric vehicles. That would be accelerating mass markets through increasing the battery range and decreasing the charging time. Okay. Another thing was for us was important tackling the EU policies in what refers to the goals for reduction of emissions in transport. Okay, and how the electrical mobility can contribute to this. Okay, and another important, last but not least point, and also that is a core part of our project, is to build or design more sustainable batteries. Okay, and you will see more information about this during today. But for us, apart from increasing the performance of the battery and increasing the lifespan, battery range, etc., is very important to make the batteries, facilitate them for second life applications, for recovery of materials, critical raw materials inside the battery, the cell, etc. Okay, so reducing the environmental impact of the battery. In all the points contribute to this. For this, our project have worked in design for circularity, so different strategies, doing a modular design, lightweighting strategies, using of recycled alloys in the battery frame, working with wireless connection, wireless communications to avoid the use of wires, reducing also some part of the weight. Also increasing performance of the battery. So if you extend the battery range, the impact we reduce the impact. And well, working also with ultra-fast charging for the previously mentioned reducing the charging time. And then also we have worked in innovation in what concerns the test procedure. So reduce the number of tests you need to perform to get the same information, and also innovating in the testing platform. Okay, this in IDIADA. So our battery is designed for easy assembly and disassembly. Enhance the repairability of the model, so you don't have to discard the whole battery. You can go and take back some modules for second life, and it's adaptable to different cells and vehicles. Okay, these are some of the details on the different points that if the presentations are public, can be helpful to you to know more or less the topics we work. No, but as I commented, recycled aluminum alloys. The design, modular design, will be explained later. Wireless bus bar, cell-to-cell connections, and this methodology to applying certain specific eco-design actions to tackle the more hotspot points that if you attack that, you get a major reduction of the impact of your battery. Okay, these have been made engaging the different stakeholders of the value chain, from the one designing components to the one designing the battery, manufacturing, and also recovering the components. In terms of battery performance, we have been working on enhancing thermal management for extending the range, also on strategies for ultra-fast charging, and combine it with the thermal management, innovations in the junction box. Today we will have the Ficosax talking about that part, and also innovating in batteries management system. This will be also presented later by a colleague from IREC. Okay. Finally, what I was mentioning in IDIADA, they have been put in place a flexible and versatile test bench that is adaptable to different platforms, and with the innovation, the motor and the battery test lab, they are not in the same place. So you don't need to have the motor in the same laboratory. You can do the test separately, and it's versatile and can simulate different kind of platforms. Okay, we will be working on this. Setting procedures for test, and also we will assess how is the end of life of our battery and how much materials we can recover and components. Okay. Okay. We are here by the end of the project. You can see outside a module of the battery, and also some of our technical colleagues are here today. So that's why I said I think we are very, very lucky here to be able to know this innovation and talk directly with the experts. Okay, we will be testing and validating our battery until the end of the project. That will be in March. I didn't put here in the presentation, but our final event will be in Wolfsburg, in Volkswagen, or in a building in the region in the complex of Volkswagen in the 18th March. Okay, well we will announce this in the social media, etc. someone have plans to visit VW at that week, we can join there. Last but not least, we are building a advisory board. We aim to engage them in the final part of the project. That means January, March, to get them on online sessions to show the results and their confidentiality agreement, of course, and get with the purpose of getting feedback from this external advisory board. If someone is interested to be part of it, we have some budget allocated for this, and we will be glad to receive your interest and assess, okay, if it's possible. That's all from my side, and enjoy the rest of the presentations.
Okay, great. So it's me again, and trying to give also a very brief overview on our project called Helios. So, okay. So Helios started as the other ones like 4 years ago, and officially we should have ended next month, but we asked for an extension. Hopefully we'll get this to finalize all the work done so far and show the demonstrators we are promising. We are 18 partners from 8 different countries, and you see on the right a mix of industry, university, research centers. Coordinator is Cornelio, who is here today. And we have a quite holistic approach. We do each and everything except the cells. The cells we buy from commercially available cell manufacturers, but all the rest, so the DC-DC converters, the thermal management, the battery management system, the cloud functionalities, digital twin, IoT platforms, this is all developed within the project consortium by the different partners. And we have also with Vestel a partner who provides a super fast charging station in order to test the fast charging. So we are integrating, developing innovative materials, design technologies. Our concept is smart, modular, and scalable, which we will prove in 2 prototype use cases, one for a small passenger car, Mitsubishi i-MiEV, which is at the Aarhus University available. That will just use the platform. And we will integrate a larger battery pack into a 12-meter e-bus at Bozankaya in Turkey and put it on the road, at least on a track. Energy density, safety, lifetime, levelized cost of storage, LCA. These are the main goals and objectives. So we need to prove during the project. And also second life and easier recycling at the end. So we hope to meet these objectives with reduction of weight and reduction of volume, very fast charging, in theory and principle, in about 6 minutes for a small passenger car, and extend the lifetime, as in the call was mentioned, up to 300,000 kilometers. So one of the differentiator here to the other projects is that we have a hybrid mixed chemistry approach. We have modules which look the same, so they are outside are dummy modules with dummy cells, and the boxes are more or less identical, at least from the outside, but inside they're different. So in one box we have the high energy cells, and the other box we have the high power cells, and we can configure them in different numbers. So 2 + 2, 4 + 4, 8 + 12, whatever you need to have a different a battery pack performance, more range or faster charging or higher performance. Of course, this requires complexity on the DC-DC, on the multi-level DC-DC side, control strategies for the balancing, also the monitoring of state of X parameters in the cloud to optimize the usage and to guarantee the lifetime. But we think one of the most important advantages for potential users, meaning OEMs or tier one, is the scalability and the adaptability to different use cases with basically modules in the same size. And we have also wireless BMS. Our colleague Alberto will present this later today with some innovative approaches here. So these are some of the technologies involved in Helios. And as you see, so we start at technology readiness level more or less 4, and we go up to 7. So we are not in the phase of really put this on the road commercially, but this would be then require another step further. But we can at least prove the concept and that it works and that it meets all the objectives. Thank you so far. And then the next speaker is Eduardo Miguel from Liberty. The floor is yours.
Okay, thank you. Okay, thanks. So thank you all for being here. There I go. So my name is Eduardo Miguel. I am the coordinator of the Liberty project. So I will very briefly present you the overall scope of this project, because we have today some experts that are going to go through the details, starting with a little bit of perspective, the goals, and some facts and figures of our project, together with some of the key innovations. So this project, as all the 4 projects in COLLABAT, except for the newer ones that recently arrived, started at the LCPAT 10 call. So under Horizon 2020 framework, the European Commission was looking for projects or consortia that were willing to work in the designs of advanced battery packs, putting on a special stress on lightweighting, crashworthiness, and electrical and thermal requirements, together with sustainable battery packs in terms of dismantling, recycling. They were also seeking for flexible and advanced BMS, what comes together with remote maintenance and troubleshooting, and also high voltage systems compatible with high power ultra fast charge. Right. Other than that, there was quite a bit of effort in terms of performance and safety related testing, and it was also specified that these developments were needed to be integrated into an existing vehicle. So from that point, these 16 partners from 7 countries gathered together, coordinated by Ukerland in January 2021, with a budget of 10 million approximately, and have been working since in order to meet these 5 objectives that you can see here. So basically, we set these 5 key performance indicators in our project. Sorry. First one would be to achieve 500 kilometers on a fully charged battery pack. Second one would be to achieve a short charging time, which is going to be under 18 minutes. Other than that, we also wanted to have a safe battery pack. We're going to talk about that a little bit later on. Achieve a long battery lifetime, which in this case was set to be 300,000 kilometers. And finally, to have a sustainable battery pack over its entire life cycle. So for that, we stated 6 different goals. Would be to have a compact and safe battery pack, which is going to be crash resistant, to have a versatile battery management system for first and second life, high accuracy state estimators that are going to enhance range and lifetime, together with fast charging, and troubleshooting, innovative thermal management system, which is going to be preventing the degradation and enable fast charging. Finally, a semi-automatic dismantling procedure, and finally, to develop future-proof testing protocols that are going to be valid for this project and other projects to come. So after that brief introduction, some of our key innovations, we did work in immersion cooling systems, active safety systems. So there you can see in the bottom left, active safety systems. Not going to get into much details in this because we are going to explain it in the later talks or in the demonstrators you have there. But it's going to be active safety systems, immersion cooling, battery pack, flexible BMS based on the Fox platform, together with novel SOX algorithms. And I will let our experts explain you better than me. And finally, since this project is getting to an end, we finished this year with the project, what means that we already have our battery finished and assembled and integrated into the vehicle. We will be hosting a final event in Mercedes headquarters in Stuttgart. So I just wanted to invite you all, and feel free to forward this invitation to anyone that could be interested in. So we will be there giving some specific talks with our results and showcasing the battery in person. So thanks a lot, and thank you.
Thank you. And from the last founder of COLLABAT cluster, the Albatross project, so I give the floor to Aishel Pilar from Yesilova.
Okay, so my turn. Welcome, and it's a pleasure to be here and presenting Albatross project on behalf of Yesilova Holding as a project coordinator in front of such a beautiful group of people. Albatross project, as like the other sister projects, is a funded project under low carbon next generation battery packs for the electric vehicles. It's just started as all the sister projects started 4 years ago in 2021, and it will be ended in 2025 with a 6 months extension. We have 21 partners in this consortium from 10 different countries all around Europe. So in which specific areas do the technologies that our partners brought to the project focus and serve? This can be divided in 6 main areas, which are the battery module and packaging, battery management system, thermal management system and sensing, material and process development, dismantling, second life usage, life cycle assessment, and sustainability. So why are all those experts come together for this project, and what are the general overview of this project, general objectives of this project? First of all, Albatross aims to further develop the BMW E3. In doing so, it has a modular and scalable concept that can be applicable to mid-size vehicles and heavy-duty and light commercial vehicles. In doing so, there are some objectives, general objectives that we aim to achieve, such as weight reduction, dismantling and recycling, flexible advanced BMS, which is applicable on different type of specs, and at the same time that BMS with a 5G vehicle interconnectivity for control and remote maintenance, and the systems compatible with high power ultra fast charging. And while doing this, at the same time, we aim to validate the battery pack into the E3 with a full scale demonstration with future safety related and performance related test procedures. And at the same time, Albatross has some specific objectives that we aim to achieve, which is 20% weight reduction and 25% charging time reduction from 40 minutes down to 30 minutes, and increase the driving range up to 480 kilometers, while having a 300,000 kilometer battery lifespan, and a 15 to 20% improvement all over the full life cycle while developing innovative sensor and advanced BMS combined with cloud-based AI techniques and very fast safety detection and prevention techniques. So these are the general and specific objectives that we want to achieve. And if you ask me what is the current status of this project, I can easily tell you that we have achieved most of these objectives other than weight reduction. And our next step is, with the remaining 6 months of the project, our next step is to first implement the battery pack into the vehicle, the integration phase. And right after, we are planning to complete the pack and vehicle testing as soon as possible. And I believe we will see the fruit of our project soon. That's all from Albatros side. Thank you.
Thank you very much. I shall, and then last but not least, I'm very glad that Cornelio, who is coordinator of Helios, but he's also coordinator of the new member of one of the 2 projects of IBATMAN. BMS cannot make it today, but Cornelio give us maybe a forecast what we need or what we will see in IBATMAN in the next years.
Great, thank you. See if I can. All right, thanks. So I must say that I feel a little bit bad about selecting this name, and I must disclose that we actually had a bit of a discussion during the proposal phase whether we should call it iBatman. I was at BID earlier today, and there is a project called Batwoman. So if you have any suggestions on how to make these names a little bit more gender inclusive, that would help. And also, just listening earlier today, so Liberty is going to finish in December, Marble in March, Albatross in June, Helios is the latest, but for good reasons. In August, it would be nice to maybe have a COLLABAT event kind of talking about all these results, but then it's going to be difficult to synchronize. Anyway, maybe we can think about just because there is so many people from the COLLABAT cluster here, and I want to thank those of you who are not in COLLABAT for joining the meeting. I'm not going to ask you to raise your hand. But iBatman. So essentially what we're trying to do is when we look at all the challenges for the BMS, right, looking forward, modeling has to get better because, well, we have a lot of more requirements going into the BMS, also remaining useful life, you know, things like that. So we're looking into higher fidelity models. New sensors, that's also a challenge. Connectivity between different BMSs across different packs. Charging, smart charging, and also transition between first life and second life. So, you know, essentially addressing all these challenges, we're looking into designing a BMS that that covers all this. So I'm only going to talk briefly about, well, essentially this is a scope of the project, and then at the end, I'm going to detail a little bit more the scope of the work packages. We started in January, so we're the junior in the team here. We have 42 months, about 5 million funding, and of course, we're looking into hitting a wide range of goals, right, on performance, safety, connectivity, security, yeah, charging, first life, second life, V2X, you know, those kind of things. So that's basically the scope of the project, right? Trying to increase life of the pack, improving the modeling, and then understanding how we transition between edge and cloud computing, kind of thing. Connecting with a wider range of applications, safety, circularity as well. So how do we transition to second life? How do we categorize and characterize the packs towards recycling? And of course, you know, trying to reduce the cost, reduce the parts, weight, those kind of things. Oops. So that is the general scope of the project. You know, again, we started in January. There is a picture from the kickoff meeting, and you know, we have the typical structure of work packages that you would expect. We go through the requirements, software, hardware, a little bit more on the integration side, and then testing afterwards, dissemination. So I think, yeah, that's what I had. On the right-hand side, you have the consortium. I think we have a good mix between academia, research centers, SMEs, larger companies as well. So, and hopefully we're gonna be able to carry the flag forward in COLLABAT. So, thank you.
Thanks a lot, Cornelio. Please stay. So we have like 5 minutes, Aishla as well. So I invite all the speakers here. You can sit, maybe it's easier, or you can stand, whatever you prefer. So we will hear in the next sessions very technical details from technical experts, but here are the coordinators of these projects, which have an umbrella view on all the different topics. So maybe chance to you for any questions, comments.
Yes. Yes. Okay, so I am Inigo from from Ikerland, and the last year coordinator of COLLABAT. And I want to ask you, which is the thing that makes for you COLLABAT something different for other clusters, or which is the positive part of COLLABAT that makes you want to continue with it, for example, or not?
As coordinator of Marvel, what I saw in COLLABAT, what I found it, apart from the typical, well, let's say typical or one of the scopes of this joint dissemination. No, we try to reach similar audience, so we increase the impact when we go together. Apart from this, that may be the common thing with other clusters, was the putting together experts facing a similar challenge or common challenges in certain aspects like testing, BMS, models, etc. Bringing them together, and at the same time they are working in each of the projects. They found out difficulties, they found out solutions. The fact of sharing this increased, I think, the impact of our projects substantially, I think. And I think it's the most interesting part, or the part that makes different COLLABAT from other kind of this kind of clusters in Horizon Europe that I've seen in my experience.
Yeah, I totally agree with that. I mean, I think that first thing you already mentioned, having 4 projects together working for not only about communication, dissemination, organizing events, and sharing information in general makes much a better result than just one single project doing it. So in that sense, I think it's a multiplicator of our resources. Other than that, something that I felt really useful is that since we are all in a very similar framework, we are facing similar challenges, even if our solutions may be different, there is a very good forum in order to ask for help, to share doubts, or to, in general, seek for guidance. So I think that's one of the good parts I felt in the COLLABAT.
For me, it's a little bit different because I've been coordinating this project for almost 3 months, but I can say that I've been participating in COLLABAT recently. Even if Albatros project has been in the COLLABAT cluster since the beginning, this is a supportive group because we've been facing with the same challenges, with the same problems, and it's some kind of guidance for coordinating the project as well.
Yeah, I also think that the dynamics in COLLABAT were actually very exciting. So I mean, just the experts coming together from the beginning, right? Establishing some of the clusters, and people just getting together and talking about issues. You know, I think that was really nice to see. We organized workshops, various other events. So this was more on a volunteering basis, right? And it worked very well. So, in that sense, the spirit of it was very promising. Leadership was also valuable, just providing guidance and all that. So, in terms of continuing it, if we can replicate, right, the same dynamics, I think it would be very good. When you look at the number of, the network, right, 4 projects times how many partners each, it's quite a bit, right? So I think it was valuable. Of course, we could have done more, but we did quite a bit. Let's see moving forward if we can rally a few more projects and just keep the same dynamics.
Okay, we have time for one more question from the audience. If not, then I play devil's advocate. Looking forward, I mean, we are very glad, Cornelio, with you in a transition phase, coming from the Helios project and leading the iBatman project. Now we have BMS on board. We are looking for 2 or 3 more, hopefully, to join this and keep this alive, this flame alive. If other battery projects are considering the idea, okay, why not clustering? What would you advise these projects? What should they do and what should they avoid? What should they not do? Based on your experience with COLLABAT, what was good and what was maybe not so good, and lessons learned, so do it differently.
Hi, sorry. Cluster level. Okay.
Yeah, I think it's not an easy question for sure, but I think that just Cornelio mentioned that the spirit was really high, really good. And I would say just try to do it. I mean, go there, collaborate with people, and share things. And from there, typically with a good group, but normally is the case, it will work. Just go for it.
So I think one of the challenges was how to be effective and talk about technical details without actually disclosing anything proprietary. I mean, of course, there are the external events, and that's very valuable. But in terms of the different experts talking between themselves, it took us a little bit of time to actually find a way to be able to share publicly available information that's relevant, right? So that's why, I mean, we tried a modeling subcluster, which didn't work. The LCA testing and BMS, those work better. So in terms of potentially what other clusters, right? What to do? It's identifying what are some of the topics where we can open the books on best practices, those kind of things, and that area has to be well defined, so that we don't need to get the lawyers involved, because then it's never going to happen. Yeah, but to a large extent, it actually depends on the people joining the meetings, right? So if they want to make it happen, then it will. Otherwise, it won't. If people don't want to contribute, then it's going to be like pushing a rope. It's not going to.
This also for the future. I mean, something that we did not explore so much because of the nature. I mean, we're one of the first clusters of this kind that was created. We are seeing more clusters now, and I think that there is a very, very good opportunity for the future to collaborate not only at cluster level but with other clusters, and make a whole picture of the value chain. Maybe clusters that are at another level and that can feed all those contributions. That would be a very good path.
Yeah, absolutely. I mean, that's the next level, the next stage. Not only staying in the same call of the projects in the same cluster, but then connecting one cluster with another cluster, and really building this ecosystem of researchers with the spirit to move towards something on the road finally, which we all need. Okay, great. Many thanks to the speakers. And then we are in time for the first technical session on battery system level.
Warm welcome. Warm welcome and very good afternoon to everyone present here for the COLLABAT event. My name is Sanjit Anuradha from research group from Iracat. I work on batteries. So I am here to moderate the session on battery system designs for next gen battery solutions. So the concept of this session is to present you with the benefits of modular battery pack designs on cell to pack variations. So to begin with, we have some 4 fabulous speakers for the session. To begin with, we have Violeta Vargas from Iracat, who's going to present on recircular design of high performance battery packs from Marble project.
Perfect. Okay, thanks, Sandeep. So I'm going to talk about the work that we've been doing in Marble across eco design and life cycle assessment, also life cycle costing, but I'm going to focus on the environmental impacts on this presentation mainly. Where's the pointer and a bit hidden. Okay, so I think we all know that we've been on this path starting from the Paris Agreement, basically. The Paris Agreement is a commitment that we all did to ensure that we stay below the 1.5 Celsius degrees of global warming. And for that, we have to reduce emissions by 50% by 2030 and reach the zero emissions by 2050. Then we have the European climate law that also is aiming to cut net greenhouse gas emissions by at least 55%. So it's a little bit more challenging by 2030. And then we have the European Green Deal, which is a strategy to reach climate neutrality by 2050. So after having all this background from the European Union and all the commitments that we have to reach climate neutrality, then we have the other background, that is, where are the emissions coming from? Where should we aim to reduce these emissions, right? Because we are aiming to very big challenges, reaching 30% reduction, 50% reduction, and even zero emissions by 2050. And this is going to be hard. So we have to focus our efforts on where the emissions are coming from. And this is how the emissions are accounted by the different sectors. So energy industry accounts for 34% of all the greenhouse gas emissions in Europe, but transport also comes with the 29% of the share of greenhouse gas emissions. So this is where we should focus our efforts. And that's where Marble and all the other projects that are here are aiming for and why they started, basically. We are trying to improve the environmental performance of batteries or battery packs. So for that, in Marble project, we defined, we applied the methodology for the eco design of the battery pack along the life cycle of the batteries. What we do is we have a methodology that is that contains an iterative process where we enforce like very basic steps. We can go along the life cycle stages of the battery pack, from raw material extraction, component manufacturing, and battery pack manufacturing, then the use stage, the end of life, and the second life. And we evaluate what the environmental and cost impacts are along these different stages. So now I'm going to explain a little bit about the methodology, and I'm going to try to go fast, even though it's been the work of all these 4 years within the project. So in 10 minutes, it's very difficult to explain, but I'm going to do my best. So the first step of the methodology is to figure or find the hotspots. Where do we have to point our efforts to? Where are the main impacts or environmental impacts or cost impacts? Where should we focus? So for this, we based our studies on a benchmark analysis for what was in the market. And we figured and we designed some templates with all the environmental impacts and where are these hotspots or main issues in the different life cycle stages. After that, the second step is to figure or align these strategies. Like now that we know where do we have to improve, how can we do it? So design a few set of strategies and that can tackle these environmental impacts. So we defined a repository of strategies in a datasheet form, including all the benefits for the environment and for cost, and what are the challenges of applying these different strategies. Then for the third step, we try to adapt these strategies to the technical feasibility of the strategy. And for that, we included everybody that was participating in the project so that we can actually be sure that those theoretical strategies can be applicable to the design of the battery pack. And once we had it, we had a set of definitive strategies that can be applied in the marble battery pack. You can see like the list of 10 of these eco-design strategies on the right corner, down corner. But I'm not going to go into further detail on this. Then we define specific actions that were based on the general strategies that we defined previously. And we came up, along with the consortium, with everybody, we came up with 14 specific actions to be applied in the marble design. So after doing all this, what we need to do is ensure that all the strategies that are being applied are also aligned with the environmental impact reduction. So for this, we applied the life cycle assessment one more time. We've been doing it all along the project from the beginning, from only defining the hotspots, and then every decision that was taken in the design field was also evaluated with life cycle assessment. And then at the end, we have two scenarios, the baseline scenario that we started with, and then we have the marble battery pack. So after applying these different actions, I'm only going to present 3 of them. I don't know how am I in time, but I think I'm still okay. So action 1 was use of recycled and recyclable materials. And for this, the design of the housing profiles, the thermal management system, and the junction box included a 60% of recycled content of aluminum. You can see here that the carbon footprint of virgin aluminum is around 10 kilograms of CO2 per kilogram of aluminum. Now, if we use recycled aluminum, this impact is reduced in a 90%. So instead of having almost 10, we have 1 kilogram of CO2 per kilogram of aluminum produced. So the reduction, after accounting for the weight of the housing profiles, the thermal management system, and the junction box that are all made of aluminum with 60% of recycled content, the reduction is a 54% reduction of carbon footprint. And this accounts for 777 kilograms of CO2 that had been saved. So this is an achievement of Marble Consortium after defining all the strategies and applying it to the major part of aluminum profiles. Also for action 2, and I'm going to present other impact categories that may be new and I haven't talked about them before, but I think it's important that we don't only focus on this tunnel vision of going only for carbon footprint. So we have other kind of environmental impacts that we should be aware of. And in this case, I'm presenting human toxicity. Action 2 was aiming to reduce the content of copper material for electronic components. And this is to reduce the consumption of copper as a strategic material. Copper is included in the Critical Raw Materials Act as a strategic one because possibly the need of copper is going to be bigger than the availability of this material. So we should reduce it when it's not needed. And in this case, it was reduced in the thermal management system, the electrical system, and the junction box in 9.5, 11 kilograms, and 5 kilograms from the junction box. The human toxicity of this aluminum at the beginning would have been 24 kilograms of, I forgot the name, dioxybenzenes or something like that, equivalents per kilograms of aluminum. And the copper one has 105 kilograms of the same. Well, so comparing these amounts and applying it to the amount of copper that was substituted by aluminum, the reduction of the impact was in 88%. So this is 884 kilograms of diobenzenes equivalents. So it's also another win for a Marble project in the design and application of the eco design in the battery pack. And last but not least, action 4 was aiming to the topological optimization of profiles. And this sounds like something that we always think that is not possible. We tend to believe that everything has been designed in the most efficient way, and then turns out that it can be improved. So in this case, the end plates, the module end plates were simulated and optimized, and there was a reduction of mass material used in a 50% in weight. And in this case, I'm presenting energy consumption as the impact category, and the reduction saved 1,926 megajoules. And that is a 50% reduction of the impact. This is also translated in carbon footprint, but I just wanted to shake things up a little bit. So after all this, our conclusions is that the methodology gave us a set of strategies and a set of specific actions for the Marble project, that this highlights the importance of integrating simulation and eco-design tools and recycled materials into the design of any product, especially from the beginning of the design of the product. The demonstration, the benefits of the eco-design were already presented in these 3 final slides. So we reduced the carbon footprint, the energy consumption, and the human toxicity, but these are only examples, and it's only 3 of the actions that were applied. So the benefits are going to be higher, actually. And the implementation of this eco-design strategy allow us to work with the stakeholders and see how the teamwork really makes the dream work in Marble project. So that would be it. I don't know if you have any questions or comments, or if it's later. It's later, then no questions or comments now. Thank you.
That was a great presentation from Violeta. And next we have Mr. Karnali Barbu from Hargas University, who's going to speak on innovative modular designs with high energy and high power cells to cope up with different driving style and different use cases. So the floor is yours.
Great, thank you. Hi. Good to see you. There we are. All right. So what I'm going to talk about here is basically the main concept in Helios. I'm going to have later in the innovation section a little bit more details about the technologies that we're developing. But essentially, the main idea here is to hybridize the battery pack, combining high energy, high power cells. Now, of course, there is a discussion whether why this is a good idea. And of course, you know, we can talk about potentially segmenting the customer space, maybe making a distinction between urban styles and commuter styles. Potentially, we can say that if one is a little bit more urban driver, then maybe he doesn't need a big battery pack, doesn't need to spend excuse me, a lot of money on buying a big battery pack, but maybe he wants a little bit more faster charging kind of thing. If one is commuter, then maybe he wants a bigger battery pack, slower charging. Once he reached work, then stays there for about 8 hours, so there is more time to charge. So of course there is a discussion from a strategy standpoint, right? What is a winning strategy here? Should one design, one size fits all kind of thing, the type of battery pack, and then potentially win with the supply chain and getting the costs down and things like that? Or potentially new technologies could be a winning game as well, and try to customize the battery pack a little bit more and address different driving style, different requirements. So I think that question is still, a little bit open from a strategy standpoint. We went the other way, and then, imagine that we have a wider range of requirements to customize the battery pack, which is why we went in that direction. And essentially, customization is between high power and high energy cells. From an architecture standpoint, we assume that, well, we can customize to a range of requirements. So one could potentially want full high power battery pack, or full high energy battery pack, or various steps in between. And also we assume that we scale up the design as well. So it's not only one size battery pack, but also depends on the size of the car. And we're moving, we have an electric bus as well. So the range is potentially from small vehicles all the way to bus implementation. So from a let's say technology standpoint, we look at different technologies at materials, component, system level, processes as well, from the design, testing, implementation. I'm going to have a little bit more on technologies later on. In terms of project specific goals, so we're looking at the weight reduction, we're looking at improving energy density, power density, volumetric density as well. Better life cycle, better driving distance, all these things. And then we're going to validate the pack on two use cases. One for a small passenger car, you have it here on the left, and on an e-bus. It turns out that in the end, we're not going to use this small Mitsubishi vehicle. We're going to test the battery pack in a hardware in the loop, because we can be a little bit more aggressive. Testing it on a car, well, in traffic, then you're going to be stuck in traffic. So in a hardware in the loop, we can do a little bit more, and then we're going to put it on the bus and drive it. And so in terms of customization, we have a range of battery packs that we can build, and of course, there's no such thing as free lunch. Power electronics are going to be a little bit more complicated to connect high energy, high power modules, and then directly to the drivetrain afterwards. So we're looking at different power electronics also for fast charging as well. As Thomas said earlier, we're basically building everything except the cells. Including IoT, digital twin, those kind of things. But in terms of architecture, we decided to modularize, to hybridize at the module level. So we're building modules which are high power only and high energy only. And then using these modules, we're building sub packs, and then sub packs are going to make a pack. A lot of words there. But essentially, we're hybridizing the pack through these sub packs, which are made of modules which are only high energy or high power. So for the Mitsubishi Mia, for example, we have two high power sub packs, one high energy sub pack, each sub packs having 4 modules, and the size of these modules is the same, and so we can customize the pack as well through the sub packs. Same structure for the bus, and you have here the pictures of the pack modules as well. I think, did we bring a module? We have. so do not forget to see them. Yeah, and like I said, they're going to be tested. So hopefully we're going to start testing in spring, both in the hardware in the loop and on the Bozankaya eBus. And fingers crossed, we're going to meet the objectives. So, great. Thank you.
Thank you, sir. That was very insightful about Helios project. So next we have Miguel from Ickerland, who's going to present on lightweight design for from cell to pack level.
Sorry, you can give me pointer. Okay, thanks a lot. Title of the presentation: Lightweight Design for a Safer and Efficient Cell to Pack. So this is the title we chose for this presentation, but I would like to see it more like a tour to the Liberty battery pack and to explain why this battery pack is like that and looks like that. Okay, which in this case happens to be a cell to pack. So if we go through the objectives that I previously mentioned really briefly, we have an objective to increase the range, to have a short charging time, which implies that we are going to be fast charging the battery pack quite aggressively. We need to have a safe battery pack, again, a long battery lifetime. So if we, from these objectives, derive what do we need for each of them, turns out that we have, or we need, a high energy density battery pack. And for that, we need an efficient space utilization and lightweight materials, right? If we also want to do fast charging in that battery pack, we are going to need an effective cooling and together with reinforced thermal runaway propagation measures in order to be safe. Again, if we want to have a last long in battery pack, cooling comes again into play, and it's going to be very important. So this is the starting point. We already mentioned that we are going to redesign a battery for the Mercedes EQC that you can see here in the picture. So how much energy can we fit into this existing frame? Actually, we have to build the battery for the frame in order to be able to integrate. So the answer to that is that a cell to pack is the more energy dense solution that we can find. Around 87 kilowatt hour in a 800 volt system. That's what we finally integrated into this battery pack. So what else can we do? We made our space utilization the most efficient that we can, but we should do something else. So we took the state-of-the-art aluminum battery casings, which are the largest parts in largest parts in the battery pack, and we replaced them by composite parts. You can see here basically are the top and the bottom covers that you can see here in the picture in the bottom right. So that means a reduction in weight. It's going to help us with the range and in environmental footprint, right? What else? We also talked about an effective cooling and a proper temperature control, right? So why do we need that? Well, we have to charge the battery pack under 18 minutes, what implies high C rates, and what implies that we have to extract that heat from the battery pack while being a safe battery pack. The cooling system is going to aid or even eliminate the propagation of thermal runaway. That's another requirement we have. And again, if we control temperature, it's going to make our batteries last longer. You can see here in the right top, difference in A-in when we do nominal charging conditions or fast charging conditions. And the difference is quite evident. So how can we do that cooling effective? So for us, our answer to that is that we used a semi-immersed spray cooling system that provides us a proper temperature control and aids with the thermal runaway propagation, right? So you can see here in the picture, I'm not going to get into very, very big details. We have Yolanda here that is going to tell us way more than me about this. But basically, we took the battery pack, we could put all the cells we could feed in there, and we immersed those cells up to a certain limit or level, sorry, of the batteries That's going to help. But other than that, we had a spray system on top of the battery, so we recirculate that dielectric, as you can see here in the picture in the bottom right, in order to cool down the parts of the cells that are not immersed, right? Some more details. You can see here the tubing in the battery, the spray nozzles that you can see here. That's the white parts in the center of this slide. And again, this whole pack will be semi-immersed in the electrolytic. Okay, so we covered efficient space utilization. We covered lightweight materials and effective cooling. We still need to tackle the reinforced thermal runaway propagation measures. So how we tackle that in this specific project? So we have two different systems. The one you can see here in the pictures, and you have the demonstrator outside, is an active safety system. And we are putting that system, encapsulating some cell stacks. You can see the detail in the right part of the presentation. And that's going to help contain that thermal runaway within a specific section of the battery pack. Other than that, in between, not all the cells, but some specific cells, we also have a passive safety system. This system, depending on how we size it, can even mitigate or avoid a thermal runaway propagation. And so that's what you can see here in the bottom right of the slide. These tests, or these results, actually come from a test in which we put a passive safety system. We initiated the thermal runaway in one side of the battery pack or cell stack that we have there. First cells got into thermal runaway, and after that we can see that we have a delay generated by the heat shield, and after that the rest of the cells went into thermal runaway. So depending on how we size this, we can even delay a thermal runaway, or we can mitigate it completely. So these systems are going to work together in combination also with the cooling system. And in a nutshell, this is our battery pack that we have here in the picture. If you want to know more, I already told you about this, but we will have a dedicated event. Not going to repeat myself. And after that, Yolanda is going to give you some more details about how the battery pack is performed. Thanks a lot.
Thank you. That was a great presentation, the Liberty project. So next we have Bon van de Van to present on modular and scalable battery pack design.
Hello, everyone. Could you pull up our slides, please? Yes, thank you. Thank you. So I'm representing here the Albatross project, and I'm going to explain a bit about the modular and scalable battery pack design and the approach we took within the Albatross project. My name is Björn van Ven. I'm from Cleantech Batteries, and I'm also affiliated with Eindhoven University of Technology. Could you go to the next slide, please?
I'm trying. One second.
No worries.
Now you see the
yes.
slide? Okay.
Yes. So I'll be giving a short overview, starting with packaging space, how we looked at requirements, how we came up with our concept and the module we ended up with, and the challenges. Next slide, please. So packaging space is always very dependent on your application. For a vehicle, do you want to also be able to use the pack as a second life application? You know, there's a lot of different EVs out there, everyone with their own challenges and their own benefits. So if you could advance the slide, there should be some more information. So in our case, we have the BMW i3 and some energy storage application as Second Life. Now, BMW i3 is a bit of an older EV, and it actually came with some challenges that we were not expecting. But the challenge you will see with any existing vehicle, or rather, especially now if we're moving to smaller electric vehicles, is that you want to cram as much as possible energy in a small car. And actually, sometimes that makes it hard to give the battery typical space. You might want to look at exploiting other volumes within the chassis, but that can be quite tricky. And actually, if you want to be able to create, for instance, home storage systems, you want your modules to be small, but having small modules has a consequence that you're like our previous presenters had, that you are creating a heavier system, because in the end, a cell-to-pack approach, or an almost cell-to-pack approach, has the best energy density. Next slide, please. So if we look at the requirements that we came up within the Albatross project specifically, besides the space, we saw that, okay, we wanted to really try immersion cooling, but in a way that's relatively light. And one of our other partners will discuss that in a later session today. We wanted to be charging quite quickly, wanted to increase range, improve energy density. It's quite typical goals, you would say, but without going to new chemistry. So purely by optimizing the energy density, by improving the packing, improving the module concept. And of course, these requirements will help to decide for the cell type, the number of cells, and the subdivision of the cells into modules or hyper modules, something like that, meta cells. Can you please go to the next slide? So we came up with a few different concepts. One is where you look at cylindrical cells, where maybe immersion cooling would be very suitable. You have a relatively high energy density, and you can scale as far as you want. You can make the module wider, narrower, shallower, taller. There's quite a lot of scalability. Whereas for prismatic and pouch cells, as you can see on the next slide, packaging is a lot more difficult. So we worked out a lot of packaging concepts for different versions, with prismatic, with cylindrical. And in the end, we found out that cylindrical cells gave us the most flexibility within the BMW i3 packaging space. So if you can go to the next slide. Then you can see, okay, we ended up with some kind of nested orientations, and that looked like, okay, that has most potential. You can clearly see, oh, we need to add some more capacity. Okay, let's add a row in the side. Oh, the pack needs to be shallower. Let's remove a row from the top. It's quite a lot of flexibility there. So if you can go to the next one. That's the concept that we remained in our view, and there was a horizontal application of 21700 cells that would give us high energy density. It would be easily scalable, like I said before, because you can make it wider and narrower depending on the application. And it allows for fluid paths through the cells, over the cells rather, for immersion cooling. Next slide, please. So we settled on a design where these cells are horizontally oriented, as opposed to in the previous picture where they were more vertically stacked. And we ended up with 6 layers of 32 cells in this case. But if you have a vehicle with a wider battery pack, this could be more. If you have a slightly taller battery pack, you could choose for 8 layers, and then your battery pack could also be shorter again. And in this, we have 16. Originally, we called them slices. Then we started calling them modules just for practicality, but actually this is also a semi-cell-to-pack approach, because these are not modules that you could use separately as such. You always need to have them together to become a pack. So that's why I like to say semi-cell-to-pack. And if we went to various configurations here, and I think you can see. Can you go back one slide? There should be some more pictures, no? Oh, must have gone something wrong with the picture that I put there. Oh, here it is. That's great. So you can see this is the one of the almost final designs that we ended up with that I had a good picture of. And you can see that these modules together, they form the chamber for the cooling. So when the modules are not connected together, there is no cooling. But only when you put them together, you create this new feature. And the idea behind this is that by putting all these things together, you create extra cooling chambers, you create features. It's every material and every part in this design has at least two functions. It's keeping the pack together, but it's also using cooling. It's holding the cells, but it's also mounting the BMS. It's all that kind of things. So that's our thinking. So it's not so scalable or modular as you might hope. It's not like you can put this in any vehicle, but the design philosophy is quite scalable. Of course, as you will see on the next slide, such a challenging design doesn't come without challenges. So, for instance, we've seen that the assembly order is quite an issue, where we have some sealing challenges, some welding challenges, and connection of the modules together, because everything is so unconventional. And especially the sealing there is really tricky, because we try to keep the sealing window between the cells, and then that means you have to seal around the cell. We might need a better solution for that. And also, if you keep this into mind, then because of all the sealing, the assembly cost and parts cost becomes quite high. So that would need some further iterations, but we think that could be solved with a slightly more spaced design. But we were stuck between the requirements for energy density and the requirements for features of the pack. If we would have a bit more space, then we could have solved this sealing issue with O-rings, for instance. And finally, we can also see that this makes it easier to reconfigure the system, because you could say, okay, I have a vehicle battery of 16 slices at 400 volt, but I want a home storage system of 48 volt. And then you take two of these slices modules, you put them together in a cabinet, and then you have a 48 volt storage system. However, repair and reuse is still something that, due to the compromises we had to make it work, is a bit neglected. It was in the original design, but it became more difficult later on. So that's the quick summary of the scalable and modular design concept that we developed in Albatros. I said any questions, but I assume the questions will come after. So thank you for your attention.
Thank you. That was a great presentation. And now I invite all the speakers for the session, for the Q&A session here. Okay, please. Yeah, you can just start with the questions you have from the presentations. Any questions?
Very much for the nice presentation. In general, we know the challenges we are facing in Europe when we are talking about cell level. You, as the coordinators of these European projects on pack level, where do you see the position of Europe when we are comparing the pack level with Chinese or US pack makers?
Well, I mean, I can say briefly for Helios, because it's a hybrid pack. Essentially, the only competitors that we know of are a Chinese company called Neo, and an US company called One. So in terms of hybridizing pack, there are not too many competitors. So in that sense, we're doing quite well. But then on the other hand, one would question why there are not more competitors. Yeah.
No, my question was a little bit more general, not for this specific project, not only on hybrid packs, but in general on pack. Where do you see the position of Europe comparing to general pack designers or makers in the US or China?
So I have I don't know if you guys can hear me. I have a bit of an idea. So I think what you see at the moment, especially in China, is that a lot of pack manufacturers are also cell manufacturers, and one of the main ones that pops into mind would, for instance, be BYD or CATL, where you see they can make packs with very long, narrow blade batteries that are very tailored to the shape of their chassis. However, I think that in Europe we shouldn't be too scared by this. I think we should keep finding ways of how can we design smarter and better integrated battery modules without the dream of having to make our own cells. So if we assume that we cannot make our own cells, I think it might actually be more challenging. But if we sit down, and especially with the OEMs that manufacture the vehicles, I think we can still compete with China and America, and yeah, just show that we shouldn't be seen as the people that missed the boat just because we don't have a cell infrastructure. I think we can make our battery pack design infrastructure speak on innovative views like we did in these kind of projects, and also by showing that we have a very, very good understanding of how to build high quality battery modules.
Yeah, thank you very much. And I have a little bit more technical questions regarding the hybrid configuration of this pack. You are using two types of cells, one for power, one for energy in general, right? So I was wondering if this type of difference comes from the chemistry of the cell or it comes from the cell design. I mean, are you using different chemistries by making energy and power packs, or you're using the same chemistry with different cell designs to give a higher power, for example, for some specific cells?
Right. It's a dual chemistry pack.
Oh, okay.
Yeah.
So may I ask which chemistry, or is it confidential? It's okay. Just I was wondering if is it LFP one of them, or
Well, the high power is LTO.
okay. Thank you.
And high energy is NMC.
Okay, thanks.
Yeah. I
Thank
mean,
you very much.
potentially one idea was that, losing my voice, instead of trying to reach Holy Grail with the supercell that has both power and energy, right, potentially splitting the chemistry and, not being that challenging on the chemistry side, focus only on one chemistry and then the other chemistry, high power, high energy separately, kind of hit those targets separately, which, maybe it's a little bit easier from a chemistry standpoint, but then complicating things a little bit more, the power electronics could potentially be another way to go. The power electronics side, it's a little bit more challenging. So, maybe in that sense, there are just two different ways of addressing the same problem, either, reaching the Holy Grail with the supercell, or making the chemistry a little bit more, less challenging, and then looking on the power electronic side. But we're still at the beginning of the road. So, cost and things like that are still a bit outside of range.
Any other questions?
I can add some comment to Cornelius' previous comment. We've also seen in Marble that with the increase of the lifetime of the junction box, for example, in a 20%, we are going to increase the lifetime of the whole battery pack at the end. So it is, again, about not the chemistry, but the system.
Yeah, definitely. Reusing electronic systems, big game changer. Sure.
Any other questions? So I have one more question regarding to modular concepts. How does modular concepts going to be implemented with new chemistries like lithium zinc or lithium air chemistry that is? Because in US they are already started production with lithium sulfur and lithium air. So how does we going to implement that in modular concepts?
So I'm not too familiar with the chemistries, but from an architecture standpoint, maybe well, if you mean by module based, maybe that's not. I don't know if this is going to be the way to go, just because it adds extra weight. So potentially, cell to pack or cell to chassis might, and then there are different ways of looking at modularity there as well. But in long term, also looking into weight reduction and things like that. The module based concept, we'll have to see if it's going to survive.
Thank you. Any more questions from you? So with modular concepts, how efficient it going to be with design for disassembly for second life integrations?
So from a hybrid standpoint, we're still discussing second life applications, right? I mean, we can disassemble the pack and look at sub packs, which are high power, high energy only. And then using them in second life applications like that. On the other hand, using the pack as it is in second life application could potentially address both power and energy type of application in a second life use case. So simultaneously maybe ancillary services or time shift, price shift, those kind of things. I think we're still evaluating that in the second life, but we have some options, which is a good thing. We're still evaluating what's the right way to go.
Okay, thank you. That was clear. Any more questions for the session? Okay, thank you. Thank you for the presentations and also for the interactive question section.
Now we have a short coffee break. It will take place here. So now it's time to go to the bathroom. We will have some coffee. Also, it's time to maybe have a look at the very interesting demonstrators that are there. So we will come back here at 4:05.
Hello, and welcome to the Albatross project, addressing the needs of the European electric and hybrid electric passenger vehicle markets. As mentioned in the previous video, the overall vehicle weight was reduced by subjecting other battery systems to modifications and extensive testing. Other than the battery system, an optimization of the battery tray was achieved through the removal of structural elements and the utilization of innovative composites and multi-material combinations to replace existing ABS. The updated mechanical design of the tray also took into consideration the chosen battery and thermal management strategies. The adaptation of a zero-emission catalytic heater also contributed for an additional reduction of the battery capacity needed for cabin heating. At the same time, a significant weight decrease is expected from the reduction of the cooling system weight. This will be possible thanks to the implementation of a single-phase thermal management system combined with an improved heat transfer. All the different strategies developed in Albatross consider the necessity of sustainable dismantling and recycling of battery packs and modules, such as materials, components, and subsystems, with safety and automation. This was achieved through a design for disassembly built into the systems, ensuring that the design of modules and total battery pack allows for easy separation. Following the same purpose, a flexible advanced battery management system, BMS, capable of being used on different types of packs was pursued through a decentralized BMS for increased reusability of main and secondary units to fit different battery topologies without changing the hardware layout. Other advanced functionalities of the BMS include the utilization of combined sensor inputs for measuring electrical properties of individual cell electrochemistry, an AI-based battery modeling system using cloud technology solutions, and development of algorithms for optimized charging, which will generate crucial parameters about the electrochemical conditions inside the cells, ensuring the safety of the charging system. Next time, we are going to analyze the developments related with the test procedures to ensure future safety on electric vehicles. Thank you for watching, and remember to follow us if you want to know more about the Albatross project milestones. This project was funded by the European Commission.
Helios, towards a new generation of EV battery packs for green mobility. There is an obvious need for smarter and greener mobility in our society, where an uptake of electric vehicles can make the significant step. But why do we urgently need lighter and more compact battery packs with faster charging and extended lifetime? The Helios solution. Imagine driving hundreds of kilometers to a customer meeting. You make a stop and recharge your EV in less than 10 minutes. Imagine driving a larger EV in rural areas, going up and down the hills. Here, you need a more compact and lighter battery pack to allow for more range and better power performance in specific driving modes without fearing your battery running out. Imagine you want to sell your EV or hand it over to your child after some years of use. With an expected battery lifetime of over 300,000 kilometers, you have the guarantee that even an older EV has value and is valid for second-hand market and will be much better for green transport than a used combustion car. And even after its first life in the electric car, with the Helios battery modules recovered, you can still use them as stationary electricity storage. For example, feed in your PV. And Helios battery modules will also be easier to recycle and recover the value materials to be reused to support our environment. Helios has an innovative solution with its hybrid modular battery pack. Using high-energy cells in one type of modules, we can provide more range. And with high-power cells in the other series of modules, we can significantly reduce the charging time. That's the Helios hybrid pack, using a combination of both. With our Helios solutions, we can customize battery packs optimized for different driving styles, so that the customer can choose between sporty, family, urban, commuter, sales rep, etc. We are now in the phase of simulation of performance, manufacturing and specific testing of our real prototypes. The achievements of Helios will be shown and validated in 2024 in 2 demonstrators, a small city EV and a full-size e-bus. The Helios project partners represent a unique team of experts in their different fields to ensure an holistic approach and best quality development of the Helios hybrid solutions. There are 18 partners from 8 countries working closely together in our project. Using the expertise of this team of partners in all these technologies and elements involved, we will create an innovative, smart and reliable Helios battery pack to meet the driver's demands.
The transport sector is the largest contributor to the EU greenhouse gas emissions, being road transport accountable for over 70%. According to the European Environmental Agency, passenger vehicles can emit up to 182 grams of CO2 per occupant in a kilometre, which can be cut to just 30 grams with the adoption of electric vehicles. To reduce transport emissions in line with the European Union's climate neutrality objectives, the Marbell project is designing and developing innovative and competitive batteries with a reduced charging time by 25% and a lifespan of 300,000 kilometers, almost doubling the life of current batteries. The battery pack being developed includes an advanced battery management system, power electronic components, a thermal system to maintain cells at their ideal working temperature through a water-cooled battery, and an ultra-fast charging solution. The batteries have an innovative design, the presence of recycled materials, and include circular economy approaches, ensuring that they are easy to dismantle, refurbish, and repurpose for second life applications, all to reduce batteries' environmental impact and vehicle weight up to 20%. Marbell, towards an environment-friendly and lightweight mobility. This project has received funding from the European Union's Horizon 2020 Research and Innovation Programme under grant agreement number 963540.
Just imagine you are driving your electric vehicle from Stuttgart to Brussels without the need to recharge it. Then you can quickly charge it without having to worry about the remaining battery life. This scenario would be a real game changer to make electric vehicles suitable for long-distance journeys.
We come from a scenario in which electric vehicles were or are limited in range and recharging time, together with some safety events that we have been experiencing in the last years.
The main motivation for the European research project Liberty is developing the next generation of batteries in Europe to meet the demands of the electric vehicle market to remain competitive. These requirements include increasing range and battery lifetime, reducing charging time and increasing safety, and are highly dependent on the thermal management of the system.
The faster we charge the cell, the more heat that we generate into the battery pack. We have to make those batteries operate safely.
To ensure this, the researchers are taking an approach that is quite innovative. The Liberty system is a semi-immersion type of cooling that uses a dielectric fluid. The upper part is cooled by dielectric fluid sprayed onto the cells through a series of nozzles. The cooling liquid then drips between the cells and is pumped back to the nozzles, while the lower part of the battery cells remain partially immersed in the coolant. A cooling system that is highly efficient at dissipating the heat generated. There is also an integrated safety system to prevent any unsafe event emanating from the battery system. The whole concept of the system ensures that the battery is kept within the optimal temperature range, even while fast charging. The cell-to-pack concept allows the energy density to increase, resulting in a longer range.
The main developments for Liberty project have been specific components, so both for the electric part of the vehicle and also for the thermal management and the packaging. So all these elements together have made an affordable solution with lightweight and also for improvement of all the functional indicators of this battery pack.
Whether the battery will live up to expectations is being validated at Mercedes-Benz headquarters in Germany.
We are finally responsible for the validation of the battery, of the whole battery system within the vehicle. So at first we want to integrate the battery in an existing vehicle, and afterwards we want to do the dynamic testing of the Liberty battery within this vehicle. For us as Mercedes, it's quite important that we make the transition to electric vehicles where the market conditions allow it at the end of this decade.
A holistic approach makes the Liberty battery a true innovation. By combining a fast charging process with a long life and a high level of safety, this new generation of batteries could further open up the market to a wider public.
AVL, it is one of the world's leading engineering companies in the world. We offer services for development, testing, and simulation in the automotive industries and beyond. Really relevant for AVL Italy, there is the activity led by us related to the manufacturing of the batteries that will bring us during this year to prototype the batteries that we have developed all together with the consortium. So we hope to a great result.
In AVL Technical Center Italy, we have set up a workflow that satisfies high safety standard, just to protect assembly operators and people that are supervising the work activities. So battery pack assembly process is modular, like the design itself. The first step is to prepare the cells. Voltage on the cell is measured just to detect faults. Then on the cells, thermal pads and thermal fin are applied. After that, we apply on top of the cell a thermal sensor that will be useful to detect some thermal runaway in the normal use of the battery. After that, we realize 6 couples of cells that will be compressed in a tool and fixed by lateral holding plates. At that point, we have a first form of model realized, and then we place on it the control electronics, and after that, the mounting process for the model is finished. After that, modules are placed inside the battery pack housing. Depending on the particular battery pack that we have to realize, we use 32 modules inside an 800 voltage battery pack and 16 modules inside a 400 voltage battery pack. Then modules are interconnected by bus bar, and at the end, a top cover is placed on each module. So then junction box, DC filter, and the battery management systems are inserted inside the battery housing. Then these components are connected to the external connector by some bus bars. Then we place on top of the battery pack the top cover, and this top cover will close hermetically the battery and the cooling system of the battery itself. So the innovative features are the modularity of the design and the simplicity of mounting. These two characteristics are very important to adapt the mounting sequence to an automated process, and also the use of novel and reusable components is an indication of the sustainability of the project. We expect as main goals the recyclability of components and materials, and the second life use of the components inside the battery pack. The modularity of the design makes simple to disassemble the battery pack to the cell level. And this means that we can reuse cells and modules for a second life cycle, or components that we cannot use anymore can be recycled and can be the base products for the reproduction of cells and other components.
Hello, and welcome to the Albatross project, addressing the needs of the European electric and hybrid electric passenger vehicle market. As mentioned in the previous video, the overall vehicle weight was reduced by subjecting other battery systems to modifications and extensive testing. Other than the battery system, an optimization of the battery tray was achieved through the removal of structural elements and the utilization of innovative composites and multi-material combinations to replace existing ABS. The updated mechanical design of the tray also took into consideration the chosen battery and thermal management strategies. The adaptation of a zero-emission catalytic heater also contributed for an additional reduction of the battery capacity needed for cabin heating. At the same time, a significant weight decrease is expected from the reduction of the cooling system weight. This will be possible thanks to the implementation of a single-phase thermal management system combined with an improved heat transfer. All the different strategies developed in Albatros consider the necessity of sustainable dismantling and recycling of battery packs and modules, such as materials, components, and subsystems, with safety and automation. This was achieved through a design for disassembly built into the systems, ensuring that the design of modules and total battery pack allows for easy separation. Following the same purpose, a flexible advanced battery management system, BMS, capable of being used on different types of packs was pursued through a decentralized BMS for increased reusability of main and secondary units to fit different battery topologies without changing the hardware layout. Other advanced functionalities of the BMS include the utilization of combined sensor inputs for measuring electrical properties of individual cell electrochemistry, an AI-based battery modeling system using cloud technology solutions, and development of algorithms for optimized charging, which will generate crucial parameters about the electrochemical conditions inside the cells, ensuring the safety of the charging system. Next time, we are going to analyze the developments related with the test procedures to ensure future safety on electric vehicles. Thank you for watching, and remember to follow us if you want to know more about the Albatros project milestones. This project was funded by the European Commission.
Helios, towards a new generation of EV battery packs for green mobility. There is an obvious need for smarter and greener mobility in our society, where an uptake of electric vehicles can make the significant step. But why do we urgently need lighter and more compact battery packs with faster charging and extended lifetime? The Helios solution. Imagine driving hundreds of kilometers to a customer meeting. You make a stop and recharge your EV in less than 10 minutes. Imagine driving a larger EV in rural areas, going up and down the hills. Here, you need a more compact and lighter battery pack to allow for more range and better power performance in specific driving modes without fearing your battery running out. Imagine you want to sell your EV or hand it over to your child after some years of use. With an expected battery lifetime of over 300,000 kilometers, you have the guarantee that even an older EV has value and is valid for second-hand market and will be much better for green transport than a used combustion car. And even after its first life in the electric car, with the Helios battery modules recovered, you can still use them as stationary electricity storage. For example, feed in your PV. And Helios battery modules will also be easier to recycle and recover the value materials to be reused to support our environment. Helios has an innovative solution with its hybrid modular battery pack. Using high energy cells in one type of modules, we can provide more range. And with high power cells in the other series of modules, we can significantly reduce the charging time. That's the Helios hybrid pack, using a combination of both. With our Helios solutions, we can customize battery packs optimized for different driving styles, so that the customer can choose between sporty, family, urban, commuter, sales rep, etc. We are now in the phase of simulation of performance, manufacturing and specific testing of our real prototypes. The achievements of Helios will be shown and validated in 2020.
The transport sector is the largest contributor to the EU greenhouse gas emissions, being road transport accountable for over 70%. According to the European Environmental Agency, passenger vehicles can emit up to 182 grams of CO2 per occupant in a kilometre, which can be cut to just 30 grams with the adoption of electric vehicles. To reduce transport emissions in line with the European Union's climate neutrality
Hola, hola. Hola, hola. Okay, so we are going to get started again. If any of you has not signed the sheet at the registration, please do afterwards, because we are collecting everybody's signature to be able to justify how many attendees we had. And we know that many people just enter without seeing the desk. So if you have not done it, please, when you leave, please do it. And yeah, we are going to start again with another session.
Okay, my name is Iñigo Gandiaga from Ikerlan, and thank you all for coming to this event, and thank you for the university to host the event, and also to Eurecat for organizing almost everything. Up to now, we have seen the general aspects of the COLLABAT project. At the beginning, just some figures of the project, then the general battery designs, and now it's time for the innovations. So it's time for the more futuristic things of the project. For Marvel, for example, we will see the switchable junction box. Then we will see the immersion cooling system in detail from Albatros and also from Liberty project. And for the Helios, we will see the energy management that they have between the two models, the hybrid system with a high power and high energy system. So I will now give the floor to Alberto Gomez from Ficosa, and he's representing now the Marvel project.
Yep. Okay, so thank you very much to everyone. In case you don't know Ficosa, I will run some slides on this. I'm Alberto Gomez, and I'm representing Ficosa's innovations on the junction box in Marvel project. I'm leading the advanced engineering activities in e-mobility Ficosa, and well, in case you don't know Ficosa, it's a multinational in the automotive sector, tier 1, founded in 1949. More than 8,000 employees. We are around the globe with in the e-mobility sector. The headquarters are only in Vila de Cabals, but we have also a technical center in Taikang, and that gives us the flexibility that nowadays, in the context of geopolitical context, the automotive sector needs. No, this is all the Ficosa customer diversification. Basically, our clients are the OEMs directly, and yeah, we are divided in 4 business units, and the one I'm in is the e-mobility one, the first one. Okay, so in e-mobility, we have 5, let's say, families of products, and the one that it's now the topic of this session, it's the junction box that we provided for Marvel project. Obviously, we took care of several of the goals of the project. One of these, basically the main one regarding junction box, is the reduction of 25% of charging time. Okay, so in case you don't know what the junction box is, it's basically the product that safely connects and disconnects the high voltage from the battery to the vehicle and from the charger to the vehicle. So it's a main product when dealing with ultra fast charging. Okay, safely of the ultra fast charging, and obviously we want to decrease the charging time. What do we have to do? Increase the power.
And if we want to increase the power, what do we have to do? Okay, so we can either increase the voltage or increase the current. Each and every one of them has their drawbacks, but obviously current, so the electrons moving around are the ones responsible of the aging of the battery, you know? So if we want to increase power and thus decrease charging time, it's super important to deal with the high voltage, okay? And obviously junction box is the main product that it's switching safely this connection and disconnection of the high voltage of the battery. Also weight, we are tackling weight here. The junction box, if we are let's say comparing it with the weight of the full battery pack, it's 10 kilograms, 5, 10, 6 kilograms. But the full battery pack can weigh up to 700 kilograms. So you might think that it's not important enough, but it is. Of course, because in Marble project, what we are tackling is the reduction of weight of the passive side of the battery, obviously not the cells, which is 60, 70% of the weight of the full battery pack. So in terms of weight, 10 kilograms on regarding the passive, let's say, part of the battery is one of the main topics. So we are dealing with the 20% weight reduction by means of replacing copper by aluminum. So maybe you don't know that, but obviously copper is one of the main materials when dealing with power distribution. And as Violeta told us in her session, it's being part of the strategic raw material. So it's one of the materials to try to avoid or replace. And by using aluminum, we are not only tackling sustainability, but also we are tackling weight. No, so for the same bus bar with the same features, by going from copper to aluminum, we are reducing 50% the weight of the bus bars. Okay, which can be 30%, 40% of the weight of the full junction box. But also the lifetime of the battery. Higher power means higher degradation, but going to high voltages to reduce the current that flows in the battery means that obviously the battery pack will not be as stressed as it should be. No? And so we are also tackling the lifespan of the battery by means of having a junction box that properly distributes the high voltage. But what were we thinking in 2020, apart from try not to get COVID or not to distribute COVID or coronavirus? We were thinking about what this project, what will be the projects, these projects output that will be interesting in a scenario of 2024, which is today, no? And we were also thinking that obviously it's not rocket science. We are increasing the voltage because we're increasing the power, but it's not like you can choose from the range of voltages in EV architectures and neither in the charging points. So basically 400 volts was the architecture and is the architecture that mainly use all OEMs, and obviously the market share of the public charging points that are nowadays in the world are basically 400 volts. And that doesn't mean that the 400 volt vehicle architecture cannot be charged at 800 volts, but it's just the current will be limited, okay? So we were thinking about the hybrid the hybrid scenario where 400 volts and 800 volts architectures will be around in our roads. And also 400 volts and 800 volts capable charging points will also be around. And so we thought, okay, what if in 2020, what if we work on a junction box that it's versatile enough to be able to provide safely a charge to either 400 volts vehicle charging at 800 volts and 800 volts vehicles charging at 400 volts. This is what the innovation we wanted to bring on the table. But as you know, today we are in the same ratio, let's say between 800 volts and 400 volts. 4 years after we submitted the proposal, the scenario is the same, or almost the same in terms of, obviously the future is 800 volts and beyond, but when this future will come a reality, really, you know. So it's applying here now. What we were thinking about today, it's the same. And so this is why some of the OEMs that now are dealing with this issue have come to Ficosa as well for this switchable feature now in 2024. So that means that 4 years ago we were not that wrong with our thoughts. Okay, but obviously, depending on the architecture, there are some challenges that needs to be addressed. And so I will just take a look at some of the challenges we faced. What did we do to overcome them, and which are the drawbacks or the next steps to even improve them? So obviously, switchable architecture means versatility for charge and discharge. So this is the junction box we develop in Marvel project. So we have 2 halves of 400 volts in the battery pack, and can be serialized and parallelized by means of the junction box in order to provide the charger 400 volts, 800 volts, and the same for the inverter. And so that means that we can go as high as 150 kilowatt, obviously, and beyond that in the charge, because the junction box can safely distribute this much power, and thus has an impact on the battery lifetime and safety. You know? And also, in case something happens with one of the 400 volts half, let's say, the other can take charge, okay, for the inverter. So, but the con, obviously, as I mentioned, future it's beyond 800 volts. That means that for the vehicle and for the charger, that means that we know this solution, it's only transitory. Okay, we know this. But also we also know that in order to have this feature in the junction box, we need to implement more components within, basically more contactors, in order to be able to distribute and parallelize and serialize all the batteries. That means more contactors means more weight. Every contactor can weigh for 500 grams, for example. And obviously, the more components you have, the more probability you have that one of them will fail or will age quicker. No? Regarding sustainability, as Violeta told you, we are going from copper to aluminum bus bars. That's aligned with sustainability, and that's aligned with trying to remove or to substitute the copper in the battery pack. But also we are reducing cost and weight versus copper. Obviously, aluminum is cheaper than copper, and as I mentioned, you can have the same features in terms of electrical conductivity with 50% less weight. But what's the con? The con is that if you know aluminum, there is a rapid passivation of aluminum layer, no, which is isolating the bus bar, no. So and not only that, some of the components within the junction box have a connection based in copper still. So we have to face 2 challenges. One of them is galvanic corrosion because of the intermaterial aluminum copper. Second one is the isolating layer of alumina that it's instantaneously formed when the bus bar is manufactured. So how to avoid that in 2020? 2020, not 2024. So in 2020, what we did was to apply the nickel coating that it's obviously going against sustainability. Okay, so that's to be clear, because once the bus bar is recycled, there will be obviously content of nickel there if it cannot be removed. And obviously in 2020 we thought of replacing copper by aluminum, but we didn't thought to replace it by recycled aluminum, no. And as Violeta showed you, there is a 90% environmental impact reduction. So this is again another next step for the future projects that we are developing in Ficosa. Optimized housing, obviously, that's a really big, this feature means really big junction box. Really big junction box means a really big housing. And so we had to optimize housing as well, or the bracket and cover. It's also called like this. And so obviously an optimized housing means less plastic or carbon fiber, or glass fiber, let's say, and also decreasing weight and cost. But what's the con? Obviously, the plastic is not recycled. So again, this goes against sustainability, no? And this is another step that we will check in the future projects. Yeah. And so yeah, that's innovations we bring. Thank you.
Thank you, Alberto, for this innovative solution to work with both 400 and 800 volt systems. Now it's time for Elios project, and Cornelius will present us the clever modeling for energy management between their two modules, and also Juan Alberto Romero from Vitesco will help him with, I think, more technical parts of the presentation.
All right, thank you. So just a quick overview. Let's see, since we're going on the technical side, let's see who we have from Helios here. So Thomas is expert on connections, bus bars, things like that. Alberto on BMS. Farshid did all the modeling, Akash and Vision, decision support system, IoT, and things like that. We also have Luis from Iraq here on testing, Second Life. So my job, it's easy now, all the technical questions. All right, but just in terms of reviewing maybe some of the technologies and a little bit more focus on EMS, I started from this slide here, essentially looking at the different innovations, maybe at material components, systems, processes, some of the methods, testing, and things like that. So we have a long list of technologies. I just cut and paste here, basically some of them. So we're looking a lot into modeling, power electronics as well, charging, converters, control, health management, energy management system, digital twins, IoT, AI, LCA. So yeah, a lot of ground to cover. Well, I'm not going to go through all the technologies here, but essentially we started from the modeling. We did a very thorough testing of the cells that we received, and we used that data to build models at the cell level, and then ramping up from there the module and the pack system level kind of thing. And of course, these models used for digital twin afterwards. We looked at FMEA, starting from the cell level as well. Excuse me, and then moving up at the technology, at the component and subsystem level. We're going to go through testing of some of the technologies and then identifying some of the failure modes that way. So we have a pretty thorough process of doing FMEA, and then based on that, decision support systems. We are looking into building a model for the whole pack, so not only at the cell level, but also including the other technologies, the TMS, BMS, energy management system, all these things. So this is going to be a pretty comprehensive simulation platform that's also going to help us, understand different, use cases, scenarios, drive styles, things like that. From an energy management standpoint, so this is an interesting problem for us because it's a hybrid system. So we need to understand, what are the optimization criteria for the energy management system. We can say that, we're trying to manage the whole pack so that the whole pack reaches end of life at the same time between high power, high energy, potentially optimizing in terms of state of charge between the different subpacks, maybe preparing for fast charging, preparing the pack for fast charging ahead of time before getting into a charging station. So for us, the energy management system and the different state machine, it's actually a bit more complex than just one chemistry type of pack. This is something that we're still working through, and then wrapping it up pretty soon and getting it into testing. On sensors, multi-sensing unit, we can take a quick break from our sponsors.
So hello, Alberto Romero from Shefla Technologies now, before we were Vitesco. So since 1st of October, I must say we are part of Shefla group. So about the sensor, is a small piece of hardware you can find out here. So you are fully invited to come over and look at it, and we can discuss. As we started in 2020, we were focusing first on the pressure sensor to identify whether if it's an overshoot of the pressure within the battery pack and trigger a CAN message to the BMS in order to wake up the system alert, there is a coin fire. We went through the Helios project and we introduced a thermal gas sensor for detecting the hydrogen creation out of the small leakages, which will be a previous step before the pressure is going to increase. As well, we were looking after the humidity. So everything is being packed, is available there. So it's a real mock-up. So it's not a functional one, but the size is exactly this one. Now we are looking also to put inside the acceleration sensor as a part of site activity from Helios project. So the first parts are available mid of 2025 with the only pressure sensor in the QM level and with safety FUSA ACLB rating by end of 2026. So if we go one slide next, yeah, you can see it anyway here outside. So here the specs, typical specs of such small sensing unit in the Helios. For the electrical bus application, we have one of them for each sub-pack. It means at the end, 8 of them, because it's where you have the pressure casing there. And they are like comparison to a €2 coin. They're pretty small things, so it's very suitable, depends on the application and fully scalable. At the end, it gets a small additional software, depending on the application, but for Helios, we have fully changed the ID of the CAN sensor or messages in order to identify which was the multi-sensing unit, which were triggering the potential risk. And I will go afterwards about the BMS in the details. Thank you. Starting to create a virus and we're starting to have increase of pressure.
All right. Moving on, also talking about fleet management system, IoT, we designed a platform where we understand a little bit better the driver behavior, maybe predict drive cycles a little bit more ahead of time and try to optimize also through the EMS, optimize the use of the battery pack. Yeah, we have an IoT platform. We're building a digital twin. We're using actually 2 platforms for this for now. One is called Digital Twin as a Service, which is released from Arcus University. It's an open source system. The other one is MATLAB-based ThinkSpeak. So we're looking at building cell models for now, and then ramping up from there on these 2 platforms, so potentially selecting one of them afterwards. But the idea is to have a digital twin for the pack, and then potentially even connect them with other packs as well, exchange data. Things like that. And then, as I mentioned before, these are going to be put in test pretty soon at Arcus University in the hardware and the loop and the eBus at Poznań. So yeah, I think that's what I had. Thank you.
So thank you, Cornelius and Juan Alberto. Now it's time for the thermal management part that will be explained in the case of Liberty project by Yolanda Bravo from Valeo. As already Edu explained before, it's about partial immersion cooling with the objective of thermal management and also safety of the battery pack. So
Thank you so much for the kind introduction. So I'm Yolanda Bravo. I'm Research and Innovation Technical Leader at Valeo, and I will explain one of our main contributions in Liberty project. So we were responsible for the thermal management system and also for the battery casing. But in this case, I'm going to talk only about the immersion cooling system that we developed for this battery pack. First, I will go briefly into an introduction, then I will explain the system that we use in Liberty and some tests, because as we have mentioned before, Liberty project is about to end, so we have already results. So we look at the battery thermal management, so it's coupled with both the power and also the cabin thermal management systems. And one of the key topics that we have to take into account is safety for battery cell operation. So when we look at the cell operation, we have a range of temperature that is optimal for performance. And if we go above or below this range, we have a problem for aging of this cell. And what is more, if we go upper than, for example, around 40 degrees, we have also a problem of safety because we will have thermal runaway events in this cell. One of the main challenges that is common to all our projects is the fast charging. So fast charging is, we could say, critical for thermal management because it means that if we have a 4C charge, it's a multiplying effect on the heat rejection that we are needing in the battery cell. So this is becoming a priority for electric vehicles, and so we have to take that into account for thermal management system. Regarding thermal propagation, it can be caused by different events in the battery pack. And one of the key topics that we have is how we can contribute to mitigate or to avoid this event of safety, which is also one of the key topics as objective in the project. When we develop the thermal management system, we take into account the cell, geometry, and chemistry. Also, how is the charge and discharge profile, and also how the battery pack is. I mean, if we have cell 2 pack, cell 2 chassis, and so on. So, and finally, this is a compromise between cost, weight, and performance. So this will be more or less the summary of state-of-the-art solutions for thermal management system and the new ones. So the ones that we have as massive serial production are those that are, we could say, heat exchangers, that we have a heat rejection by contact. And then we have immersive cooling. Immersive cooling enables a higher heat rejection capability, and also it improves aging because we got a better homogeneity of cell temperature. So if we look at, as has been mentioned before, the system that we have used in Liberty project is a partial immersion because we have an spray cooling. Then we have these sprayers, which are in the upper part of the battery pack. And then we have different benefits of that. First, we are going to reduce the battery weight because we do not have the fluid that covers all the battery pack. And also we have we could say, an additional effect on heat rejection because we have this spray effect on the busbars. And for sure also the cost. So this is the application on the battery pack of the Liberty project, and we have not just the piping and the spray, but we also develop the whole cooling system. That means that we have the oil cooler, the pump, the filter, and the valve, because there is also a diversion that goes to the battery main switch to cool the component. So we do not have, we could say, an additional volume with that, and we got a good packaging effect with this system. We must take into account different things because as we do not have the full battery pack immersed, we have to tackle with the fact that the vehicle will go in different slopes. So we have to validate which are, we could say, the suction holes, because we have to, I mean, the fluid is heating up when the cell, for example, is charging or discharging. And then we pick up from the bottom, and then we go to the cooling system, to the cooling loop. So we have to ensure that all the cooling, all the electric fluid is going to be collected, and we have to do different trials to validate that. And also we have to be sure that we have a good flow homogeneity in our system. So that's the reason why also we made different simulations and tests to define how the sprayers are distributed into the battery pack. This is an image that you can see with the whole battery pack, which is already assembled with the system. So we also installed some glass windows to see which is the effect. And you can see here how the sprayers are. So they were previously simulated with different techniques, and we see that there is a good performance in the real demonstrator. And also we have made a whole system, a whole simulation model that takes into account the cell that we are using. So we took the battery thermal model with the cell, and we have all the relationship with the vehicle also, because we have to integrate that in all the system of the vehicle, in this case, the Mercedes EQC vehicle. And we have also the whole system and the whole optimization. And there is the first simulation that we did to verify that the cell temperature is not going to go higher than 40 degrees. And if we go to the results, so with the battery pack already mounted, so this is in our partner, in one of the partners of Liberty Project, which is Flanders Make, that has been doing the test on the whole battery pack. And you can see here the installation. And if we go, you see here some images of how the operation of the thermal management system is. So for fast charging, which is the most critical condition for the thermal management, is 300 kilowatts and 2.33 C. That corresponds to the main objective of time for charging, which is 18 minutes. So if we go to the 300 kilowatt test, we have 20 minutes for going from 10 to 80% of SOC. And we have the temperature of the cells that we see in the third graph that are below, in all cases, of 40 degrees, and with a difference between cells of 6 degrees. So it's fulfilling well the objectives. So here, this is also an illustration that has been made by Flanders Make, that we see that we have a good homogeneity as far as we are increasing we are going through the process of charging. And this is also corresponding to the other fast charge test, which is the 2.33 C test. And here we have 18 minutes, which is the objective of the project. So this is okay. So we can say that we have done it. And one of the key topics that I mentioned at the beginning is safety. So we did not with the whole battery pack because we had only one, but we also did some destructive tests with some mock-ups, and we show that the thermal propagation is not occurring with the immersion cooling system. So I think this is one of the key topics in this project also, to verify which is the safety. So this is the explanation of the immersion cooling system. So thank you for your attention. And
thank you, Yolanda, for your presentation about the immersion cooling system of Liberty. Now it's time for Albatros project. We have remotely Povian. I'm not going to tell the surname. I will let him to tell it. It's really, really difficult. So he's from the University of Nottingham, and he will share with us the advancements in the immersion cooling solution that was partly explained before in the battery pack design. So, Povian, you can hear us?
We don't see you, Puyan.
Can you hear us? Now it's turn for Albatros project. Okay. We'll wait a couple of minutes. Okay, so
Yes, can you hear me now?
yes, now we can hear you.
Yes, sorry about that. I guess I need permission.
Okay, so we just introduced you from the University of Nottingham for the Albatros project, and you will explain us the immersion cooling system of your battery pack. So you can start. I think that you are going also to share your screen. Yes, we can see it.
Okay. Good afternoon, ladies and gentlemen. My name is Puyan Talebizadeh Sardari. Sorry for the very long family name, as you said. I'm going to talk about partial immersion cooling solution for lithium-ion battery thermal management. Dr. Surajit Sen, Professor Antonio LaRocca, Professor Alistair Keynes, and Dr. Antonio Pacino are the other colleagues from the University of Nottingham involved in this project. The content of my presentation are as follows. First, I'm going to present a brief introduction on Albatros project and the objective in this project. Then I talk about thermal management challenges and the advantage of partial immersion cooling. Then I'll talk about cooling method in Albatros, the methodology, and the module arrangement simulations I have done. And finally, I provide you with thermal management, with the new thermal management system layout and the pressure drop calculation that we have done. And finally, a brief conclusion. Well, Albatros. Advanced lightweight battery systems optimized for fast charging, safety, and second life applications. Albatros is a European-funded project held with more than 20 companies and universities in Europe. We have a lot of objectives in this project, such as reducing charging time, increasing the energy density, and weight reduction. So in this table, you can see what we are looking for. We are going to change the battery module and thermal management system in BMW i3 and increase the energy density by 40%, reduce the weight by 20%, increase the capacity by 30%, 25% reduction in charging time, and finally 60%, up to 60% improves the range that the vehicle can have. Well, as a brief introduction, as you know, all electric vehicles have a battery pack which store the electrical power to be then released to the electric motor for driving the vehicle. The battery pack combines different modules, or in some cases, just we have a battery pack without any module, which includes several cells, different kind of cells. The main limitation that we have in electric vehicles in the range and the charging time that they can have. So the solution is increasing the number of cells, increasing the power, or even changing the battery itself and using more advanced technologies. But each of these solutions has a same problem, which increases the heating in the battery pack. As you know, when we charge or discharge the pack due to chemical reactions happen in the cells, we have heating, and to increase the performance and to prevent thermal runaway, we need to reduce this heat. And immersion cooling. Immersion cooling is one of the promising technology to remove the heat generated by the batteries and maintain the temperature suitable in the battery pack. As one of our colleagues said in her previous presentation, the advantage of immersion cooling is high cooling efficiency, low charging time, and uniform temperature distribution. In this technique, we fully immerse the batteries with dielectric fluids, which is then used to remove the heat from the pack and maintain the required temperature in the pack. But the main challenges we have here is the increased weight and space using immersion cooling. So the solution that we have in Albatros project is using partial immersion cooling to reduce the weight and space. So the methodology that we have in Albatros is using a battery pack with 16 modules, and each module has 192 cells. In this slide, you can see the you can see the schematic of the cooling loop. This is the initial design that we have using a refrigerant loop to remove the heat from the core, and using dielectric fluid loop to reject the heat from the battery pack. We are going to use MyVolt DF7 due to its superior properties as than dielectric fluid. Here we have a heater which provides suitable temperature, initial temperature into the battery pack, especially in the cold days in the winter. So the concept of partial immersion cooling that we implement in Albatros project is shown in this slide. We plan to, in each cooling chamber, we plan to cool 1/3 of the cells at the bottom or left side of the module, and 1/3 of the other series of cell at the other side of the module in the cooling chambers. And with this method, we can save the weight of the thermal management system, and also at the same time, we try to maintain the same temperature similar to the full immersion cooling. And as you know, in the tabs of the battery, we have more heat, and also we have a heat generation in the bus bar. So at the same time, we are cooling the bus bar and cooling the main heat source in the batteries. We have a fully comprehensive analysis on the module arrangement and studied different arrangement considering 16 parallel modules, 16 series modules, or combination of parallels and series modules. And this is the computational domain that we have in the numerical and CFD simulations. As you can see here, there is a big challenge between the pressure drop in the pack and the average or maximum temperature of the pack. By increasing the flow rate, the pressure drop in the pack increases, and at the same time, we have a lower temperature across the pack. So finally, we reached the point that choosing 4 series and 4 parallel modules in the pack is the best solution to have a suitable pressure drop in the pack, and at the same time having a low temperature distribution. And also note that we are looking to have a more uniform temperature across the pack. So cell to cell temperature difference is another criteria that we are looking for. So as I said, the pressure drop is one of the major issues we faced. So considering all the other components that we have in the pack, including the manifold, the piping, the heat exchanger, the valves, and etc., after the precise calculation of the pressure drop, we found that we need a pump with a heading of 2 bar, which is actually a huge number and needs a powerful pump. But due to the limitation in the power of the pumps, available pumps of the car, and also maximum flow rate, we reached to a new design for the thermal management system of in Albatross project, using a separate dielectric fluid loop and a separate coolant loop and an intermediate water glycol loop. So in this way, we can increase the pressure drop tolerance in the dielectric loop, and at the same time provide narrower temperature distribution, temperature at the inlet and outlet of the battery pack. And also at the same time, we can have a better control on the inlet temperature to the battery pack. So this is the thermal management system that we are going to implement in the BMW car later on. So as a conclusion, we conclude that partial immersion cooling is capable for thermal management system. We found that the average temperature of 33 degrees during fast charging can happen with using the high flow rate of 85 liters per minute. And high pressure drop happens because of the high flow rate, which requires precise cooling of the thermal management loop. Thank you so much for your attention.
Okay. Thank you for your presentation. Now, please, Yolanda, Cornelio, and Alberto came here, and we can do it. I think a stand-up is easier, faster, because we only have 5 minutes for a couple of fast questions. Does anyone has question?
There's a question to Alberto from Ficosa.
Yeah.
This switchable battery module, it's feasible, it's makeable. Did you take into consideration during the project the differences in the C epsilon capacitances when you are switching from 400 to 800 volt system? Did you take a look into that?
Yeah, we took a look into it in the requirements phase and in the system definition, let's say.
Hello? Yeah, okay. So for the last presentation, sorry, but not able to pronounce your name. A really short question about you. You mentioned that you refrigerate roughly 1/3 of the cells you have in there by chambers. So how do you do that isolation in terms of feeding those cells in the channel without any leaks or anything like that?
Actually, leakage is the one of the main issues we have in Albatross project, and we are not responsible for that problem, and another company is doing that, but they study different modules and so doing different tests to prevent leakage. I don't know actually how they manage that, but I know that they test different modules and finally solve the leakage problem.
Okay, thank you.
I think we have time for one last question. Yes, of course.
This goes then to the Liberty project. Did you analyze what's happening with the wearing of the fluid you're using for the cooling? What's happening? Are you thinking about a service concept of changing the fluid over 3 years, 4 years? Are we bringing back the vehicles to the garage every 2 years from now? Because as of now, I didn't visit it.
Yeah, this is something that is in progress. I mean, for inside Liberty, we have not been doing any durability tests. So what we have done in parallel are some wearing tests for the fluid and also electric staticity test. But this is something that we have to work further to know which is the whole durability. But this, in fact, was not included inside Liberty. It was not possible because finally, as you show, the last tests were just performance, but this is something that, I mean, this is a very good question, in fact. Yeah, the next step, as you mentioned. Thank you. Yeah.
Okay, so thank you for the 4 speakers and give them an applause, please.
Thank you.
Now it's time for the last session that will be moderated by my colleague Edu. So.
Oh, okay. Thanks a lot, Inyo, for the kind introduction. So, last session, it's called the brain of the BMS. BMS, the brain of the batteries. So, after many discussions, many meetings within COLLABAT, specifically within the BMS subcluster, really happy to share with you all today at least a short glimpse of what the COLLABAT projects are going or have been developing, what are their BMS concepts, the problems they have, the solutions, and additionally, we are really happy to host within this session the new coming projects for the COLLABAT that they will be giving us more detail on what innovations can we expect for the next years to come. So that being said, I would like to give the floor to Sergio Brado Rey from IREC, representing the Marble project. So thanks a lot.
So good afternoon. Thanks for being here. Thanks for the nice introduction. Today, I will start this session talking about the advancements that we did in Marble project in regard of the development of a new generation of battery management systems. Very briefly, this will be the section that we'll be covering today, and just to stick to the time available, going directly to the point in terms of BMS technology, Marble framework focuses on giving closer electrical vehicle batteries to sustainability, assessing mainly 2 key areas. One, which will be the extension of the energy use that we can make from batteries, and also the other one which will entail how we address and how we can optimize all the process from transitioning from first life stages to second and posterior ones. So, but first, between to meet these objectives, for the first, we need to establish very certainly the amount of energy available at every moment in our batteries for in all its lifetime. So for doing that in battery complex systems, we have BMS software, and with software I mean battery models that we can use to perform and calculate the exact state of our batteries. If we improve the accuracy of these models, we also have been improving the insights that we can extract from our battery and use better our systems. And effectively improving it, we can see benefits in the decision making along all this lifetime of the batteries. In terms of modeling, we can choose between different options. There are many, and the decision of which is the best one for our application, it's a very key point here. So for meeting the second objective, the key point also is address the complexity from pack to cell structures, meaning that for doing all our estimation and not knowing the state of our batteries, we need to do different measurements And considering the huge number of cells integrated in a pack, we have many sensors. And these incur directly in terms of wiring in battery resources and materials needed for developing it. And also represent a very significant part of energy consumption of the total the overall BMS. In terms of meeting sustainability, it can be a total pain. So what Marvel proposes is to address these two areas. One is hardware and the other is software. And with that, providing a better EV battery, more oriented to an eco design that further aligns this pack with sustainability, focusing on a flexible and modular system that allow us to operate better the different modules that we have inside the pack, and also serves of wireless connectivity to reduce the materials, further aligning with the second objective of Marvel project. So in terms of the configuration that we have different battery module units inside our battery module. Each of these battery module units is controlled and has its own microcontroller that allows to perform low-level control operations and also simple estimations, such as the SOC. This represents the BMS slaves in our system. These BMS slaves are connected in two strings, are controlled by two supermasters. These two supermasters act as the BCUs of the system, the battery control unit, and allows to operate in the voltage range attached by the junction box, and also manage and optimizes the energy flows between the different battery modules in the battery. Also, these supermasters are externally connected to a cloud-based server, which allows to allocate there more more complex model structures that allow us, with data-driven approaches, calculate much better SOH, and in that sense, make the system able to adapt to degradation, updating all the embedded part and the embedded local system. Highlighting that this embedded local system communications operate totally wireless using Bluetooth technology, further seeking the second objective for BMS in this project. But the cool part here is that the flexibility that the BMU modules provide, which what makes is that we can track and know, thanks to this new advanced and hardware and software that we developed, track much better how these battery module units approach the end of life and calculate its state on all this process. And also, adding to this, the same software architecture developed allows to easily update and configure and readapt the same system, the same battery module units, to new configurations outside the pack, because it can work in there, but also we can consider this to think of new second life applications in the that we can consider. Also, taking into account that these battery module units can work standalone outside the pack and can be serialized up to 1,000 volts, there are a wide range of reusability potential applications that we can consider. Also, taking into account the wireless and simplified material in terms of materials structure of the pack, allow us to have more traceability and control on our module, and can further help to align this system with the upcoming EU regulations, such as the battery passport. just finishing with conclusions very quick. What BMS in Marvel project does is to provide an eco-design battery pack, full operative, that aligns with industry standards, so it's expected to be well received in market. And also, all these modeling and software in terms of hardware and software structure developed here promises to set the new standards that the next generation next generation of BMS will have. As future work, as Eduardo said before, we are starting the testing process of all the overall system, and also advancing in and assessing which are the further increasing the accuracy of the models that we can embed it in the local system and also in the cloud-based system. And also, we are evaluating different applicability scenarios in terms of Second Life. And that was all from my side. Thank you very much.
So thanks a lot, Sergi, for your nice presentation. So now we will go for another wireless approach by Juan Alberto Romero from Sapler, which is entitled Scalable and Modular Wireless BMS for Mixed Chemistry Approach and Different Balancing. So, floor is yours. Have your... There you go.
So, hello, Suzaman. Hola, buena tarde. Hello, everybody. Thank you for the invitation for being here and talk about a little bit of the wireless BMS we have deployed in the Helios project. So we should have before Vitesco colors, yellow color. Since the 1st of October, Vitesco Technologies is now part of the Scheffler Group. So we were acquired or merged beginning of October officially. So since then, we are living this wonderful yellow green color in the future. So yeah. So when we are talking about the wireless BMS, we can always differ what it's about the cloud on or what we can do with more calculation power and the cloud services, or what we are doing here in the Helios is to connect the local BMS with the cell supervisors in a wireless manner to avoid the wiring harness across the battery pack and having a better scalability and modularity of the product with the need for the Helios. So Helios, we want to mix LTO and NMC modules and module-based. And we want to have all flexible approach as much as possible. Okay. So the idea behind is we track individually for each of the cells out of each of the chemistries, all the parameters, the cell parameters, how they are aging over their lifetime, the SOC is the state of health, state of power, remaining useful lifetime, and the state of energy. And we interconnect it together with the energy management that Cornelio spoke a little bit before, so that we can drive at the end the battery pack in the best manner, in the most efficient manner, either for efficiency behavior, either for maintenance of the battery pack, temperature handling, or CO2 approach, or any what might everybody understand under this brain in the future. Here you can see a small overview how the architecture of the battery pack is looking like. So the LTO modules are connected to the electrical powertrain. So what the vehicle sees are the LTO chemistries. And these LTO chemistries are providing the peak of the currents plus the mean value, which are provided through DC-DC converters with the NMC modules. So the NMC chemistry is providing the range, the LTO, the acceleration, and the acceleration of the vehicle. These DC-DCs are also scaled towards the needs of the particular vehicle, and the approach is fully scalable. So we can have 4S2P here, we can have 4S1P like we have in the MyF vehicle from Aarhus University. We have up to 32 nodes. Oh, I'm coming back. We can have up to 32 nodes of the wireless system, which is the edge of this technology in this approach can drive. So at the end, the question is, am I able to get all the values in time to compute the state of X in time? Are these values synchronous with the current measurement? The answer as of now is yes, we are able to do so on the lab range. So we will show you a couple of lab measurements as of now. So here's the structure that we developed together with Arshid Nasheri from Aarhus University. We are about to publish a paper very soon about that. Just a couple of Kalman filters, not very well known there. We have the regression linear system to adapt the DCM factors there. And the advantage of this scalability of the Helios BMS is that we can drive it individually per cell, and we can get updates out of the cloud. So this is how it does look like for this year. So we started at the beginning of the year with implementation of the features on the software in the loop, hardware in the loop, how we could call it. In the second quarter, we delivered the first parts to Aarhus University and our colleagues. Over the third quarter, we were integrating into the module. So we have the first mockups being integrated with real measurement of the cells, finding the first findings in the early stage before we triggered the complete batch of the modules needed for the two prototypes, the electrical bus and the passenger car. And over the end of this year, beginning of this next year, and up to the project extended till August next year, we're going to validate the both prototypes in the passenger car and the electrical bus. So here you can see how one small test bench does look like for the commissioning. So we have the central BMU there with the current sensing device. With some actuators, we communicate with the middle picture where all the CCUs are being racked. So we are capable to interconnect that to a hardware in the loop system and simulate all the individual voltages measurements and reproduce in a hardware in the loop environment the behavior of the cells before having real cells there. So we were alive and running since several months. This is from July, in fact, that the system is calibratable through the very well-known Inca. So you can use Inca or Vector toolchain. So we used Inca in this case. So the thing is alive and running. On the left side, you see one robustified housing for the battery management controller, which is being rolled out for the electrical bus application. It's a little bit bigger than expected. It's also sealed because the electrical bus application does not have sealing on the battery pack. And on the right side, you can see two kind of balancing approaches. So in this application, we have separated the sensing lines from the balancing lines of the supervisor unit, so that depends on the application, passenger car or electrical bus, we can use and calibrate different passive balancing approaches. Of course, we could also think in the future to extend it and use active balancing approach there. For this first approach, we follow only passive classic balancing into mirrors, 100 milliamps, something round about, and then a peak of 1.7 ampere for the LTO modules. Fully scalable, fully calibratable, everything for the lack of the calibrator, which is going to work on that. Yeah, is where my job finishes there, you know. And yeah, as of now, we have 32 nodes active and running, which are getting the values in 100 milliseconds. We can measure up to 512 cells. Everything got in 100 milliseconds, and we can get further values like the safety value out of the chip in a slow manner. Temperatures, no need to get it faster, but anyway, we're getting it in 100 milliseconds because we are engineers. So the wireless link, as of now, over the desk, 1.5 meters long for the passenger application we tested. Here you see on the left side the housing of the central VMU. On the right side, you see the cell supervisors. And here you can see some values of the upstream, downstream link with the wireless system. The values are pretty kind of stable. So below -50 is what you're starting to lose the strength, and you start to communicate, to retry to communicate. It didn't happen to us up to now, so it worked pretty much. So we went to up the maximum possible numbers, so 32 nodes. And the link is still pretty stable, 1.5 meters distance. We know that the electrical bus, in the roof of the bus, we will have a little bit more length, but we are pretty confident this is going to work. And why I'm pretty confident? Because if I have time, I would like to show the video. So before we start, we see here the long stream. You see -84, which will be the CSU will try to retransmit. Okay, and we see the upstream. Some of them are by -4, and some of them are by -80. So 2 of them are trying to retransmit, but the link is still paired. Okay, now the question is why they are trying to retransmit. Come on. Yeah, please. Okay, so this is the first measurement. So I will ask you to stop it now for a second. Okay, here you can see the first CSC, which is externally supplied without real measurements of the values. If you go a little bit further, we see, stop. I know it is going to be tricky. I wanted to try. Okay, stop it there. We see the second CSU, which is wireless connected and giving the results towards the central controller unit. Those are the 2 ones with -40. It means they are closest and they have the best link. Now let's go for a walk. Let me go over the colleagues. So we are around 3 meters, 4 meters, 5 meters, 6 meters, 7 meters, 8 meters, 9 meters, 10 meters, 12 meters, 13 meters away. So really at the very end, yeah, 40 meters away, the 2 CSCs were externally supplied, like the first one, having the try attempt to retransmit, but still within 100 milliseconds, we're trying to give the values back. Of course, this is a kind of engineer scenario that the engineers do look like to test. It's not a real use case, of course, but it gives you the thing. Maybe for stationary applications might be a use case. But for the electrical buses, give us the first confidence that this system will work stable when we are 2 meters away and still in the same kind of housing. Yep, that was all. I'm happy to answer questions afterwards. And we have a couple of pictures and the small prototype of the MCU outside. So yes, that's final thing that the people see that it's consuming current, so it means that we are working. Yeah? Good.
Yep, so thanks a lot for that presentation. Okay, so very nice presentation with nice videos that are really, really helpful at this time. So next speaker, my colleague Íñigo Andiaga, with the presentation entitled Advanced SOX Algorithms Using Transfer Learning from Real-Time Operating Data. So Íñigo, please.
Okay, so the BMS from Liberty project has been developed by Fraunhofer IASB, by Ikerland, so we are not going to explain their work in details, but as you know, the battery pack is running, and we have been working from Ikerland in SOX algorithms, and I don't know if you are familiar to this kind of algorithms, but if you are, I know that you have sometimes think about, okay, I want a generic algorithm, not an algorithm that I need to recalibrate or change from LTO to NMC, like in the Helios project, for example, if the Helios have a common algorithm and even more for LFP batteries. So we started to think on that, and okay, we have different applications, different batteries, and we need different algorithms, a lot of lab testing, a lot of work. So what we want, what was our innovation, our idea? We want to have a universal algorithm starting for a small model with a really quick modeling phase, and then a small experimental burden to adapt this model to ourselves. And we start thinking, okay, can we use this model to different cells? Can we have this weak model and then become more accurate and improve it with field data? And we thought, okay, I think we can do it. I don't know if in an engineering scenario like the one explained by Elios, but at least in our computer, we are trying to do it. So our methodology, we started with virtual data set. So we started with a electrochemical model, for example. From there, we can have a lot of information for a certain cell. It's like a common cell. This gives us the opportunity to have a lot of data without needing to test them. Of course, we need to have the model, but not once that we have the model. Then we can have the data-driven retraining to have a more accurate model. And after that, we can also adapt it to new cells using transfer learning. So this is what we did in Liberty project. So we have data set based in LCONNC cells based on an electrochemical model. And then we have the Liberty cell, which is an NMC cell. And we did a lot of lab tests. So like this, we can test our approach with a complete NMC model. Okay, so what we did, we have the baseline model in the stage 1 based on the electrochemical model. Then we have a transfer learning, using transfer learning techniques. We adapted to NMC cells using only a part of the test from the Liberty project. And on the other side, to compare our results using transfer learning, we have a complete NMC model with a lot of tests, the things that you can do in a European project. And then we have the same reduced test that we are using in the transfer learning, we use to develop a weak model. And then we are going to compare if the transfer learning model is better than the complete one. That's difficult, but it seems that it's easy to have better result than the reduced NMC model, which is using the same data, but without the previous knowledge of an electrochemical model. Okay, so these are our results. In the right top, you can see the results for the SOC estimation from a reduced NMC model. So when we are going down on SOC, we are having less accuracy, we are accumulating error. But if we apply the transfer learning techniques to this model, you can see that we are able to reduce the error. And if we go to the SOH algorithms, here we tested with the same reduced NMC model, but we tested also against the complete NMC model and the NMC with transfer learning techniques. And here we learned that as with the electrochemical model, we are able to reproduce a lot of data. The transfer learning model was even better than the complete model based on NFC data from the lab. Of course, we have a lot of data from Liberty project, but not all the scenarios that we can test. And because of that, in some cases, it was better the model with only an adaptation using transfer learning techniques to our NMC cell than the complete NMC model. So as conclusion of this short presentation, SOX estimation algorithms can benefit from transfer learning to enhance their adaptability, performance, and efficiency. The methodology serves as a basis to develop new algorithms, ensuring its consistency and reproducibility. It outperforms comparing to other models using the same data and even using 50% more data. So we are using 50% less data and we are performing better than the complete algorithm, and transfer learning shows as an effective strategy, emphasizing the reduced data requirements, improving the results, and having shorter training times. Of course, all this in our computers, then we need to think how to do it in a real scenario with real cars and all the data coming up and down from the BMS to the cloud and all these things. This was all from my side.
Thanks a lot, Inigo, for your presentation. I will just introduce the next speaker. So it's going to be Theren Akar from FEB, representing the Albatros project. And there you go. So.
Okay, thank you. Hello, everyone. This is Shanatar from Turkey. I'm working in the Albatros project as a technical project manager. And today I'm going to introduce you what we did in Albatros project, what we achieved, what we try to achieve also. Some parts have final, not finished yet. Let's start with Albatros introduction, but I will going to focus on especially which BMS problems we focused on and our solutions and the summary of Albatros outputs as a result. Let's start then. As many of you, our aim was same, reduce the charge time, increase the performance, and increase the range and increase the capacity of the battery and etc. As we mentioned by our all coordinators as well. So we come up with new BMS solutions. It means it's again regular BMS solutions, modular with CMU and the master unit. In the master unit, we use system on chip based microchip to improve our battery master for more to run more complex algorithm on it. It serves like a software defined vehicle also. In the future, if there's a software defined vehicle available, you can run all your complex algorithms in the software defined part, and your BMS won't be there anymore, according to our estimation. And about the SOX algorithms, I'm going to mention here, we focused on SOH and already mentioned our sister projects also. We also have a solution SOH on the cloud platform. We have a anode control charge algorithm, and we have a Kalman filtered state of charge algorithm. I'm going to give some details of them. We mentioned too much sensors and too much information towards the BMS master unit, and right now I'm going to introduce new sensor that we bring into our CMU. It's electrochemical impedance spectroscopy sensor. It's a normally device, laboratory cell testing device originally. And normally in the laboratory, if you are going to cycle test on your cell, you can use this device. And with this device output, you can understand your cell aging very accurately during the time. And we put that guy in our CMU unit. In the CMU, we have a small chip, very small area. It a little bit make our hardware larger, but only 2 centimeters, something like that. And it can do measure or EIS test on the every cell for 24 series. 24 series coming from the CMU. Our CMU hardware is right now controlling up to 24 cell. Because of that, it's coming from there. And with this measurement, originally, I cannot show it. The left part, EIS output from the laboratory device. It's a very, the left one. Thank you. In the laboratory, those devices are bigger and their capabilities are bigger. In the right part is our our result, it can be, how can I say, improvable to make it same data with the left part. But yeah, in our first hardware solution, our current circuit system working that way, but we can extract RC parameters weekly or monthly from with these devices. I'm saying because monthly you cannot use this sensor during operation. Only parking time you can use it. So, but it giving you RC parameters directly. Those RC parameters won't change in a cell very frequently. So with this new sensor, we introduce our algorithms on top of that. It's a very familiar maybe graph for the other projects as well. Initial values is in our initial values coming from EIS. In here, we are getting measurements and we are using dual Kalman filter, some AI methodology, small AI for SOC, and we are calculating SOC algorithm with this, bring all of these different algorithm positive advantages into the picture. And right now, we couldn't have a chance to battery pack test yet, but in cell level testing, we achieved 1% accuracy with this methodology, but it's a cell level. It's not a promise because of that. Then I can continue with the anode control charge algorithm. It's a little bit, this one is a little bit tricky. Anode voltage is a cell inside voltage measurement. And if you don't have any reference anode in your cells or any sensor inside your cells, you cannot make it real-time measurement of it. So we make an AI model, and in this AI model, we train those model with anode voltage potential with different scenarios. And with that information, we are estimating anode voltages, so we can increase our charge time according monitoring the anode voltages. So if you are seeing anode voltage comparison in here, one of them is chemical model, one of them is our AI model. The main topic in here with anode control charge, we improved cell level charging time 25%. In maybe real pack, it will change a little bit, maybe 20%. It could be reduced according to pack, how can I say, size. But you are with anode control charge. I'm not talking thermal runaway. I'm talking fast charging without aging the cell faster in normal condition. Next topic, SOH algorithm. SOH algorithm is also very similar with other projects. We just introduced this methodology on the cloud because SOH is not changing very frequently. We created AI model, and in that AI model, long short-term memory methodology is used. We trained our AI model with different charging scenarios, discharging scenarios, lots of data. In our project, we use 400 to 700 cycle information from cell, and also we have another LFP cells information as a company. So we trained our model with 2 different cell data, and our accuracy is lower than 1% in the cloud power computing power. Last part, maybe small part during this project. As you know, we are using i3, BMW i3, and in that i3, unfortunately, there is no telemetry unit, so we have to find a solution for it as well. In this part, we use some regular hardware, create a telemetry unit, and in this telemetry unit, we bring this closed system architecture, big data transmission, AI models, managing and communication between the vehicle and the cloud server. During this project, also we are collecting 1 Hz data from the BMS. We also learned that the transfer the data that frequent is not very easy job, but we have some data concentration and network management solutions. So we are able to achieve this connection to this sending data to cloud side. In here you can see, I don't want to go over details in here. Cell monitor unit that I mentioned that we bring the life into this project. Apart from the electrochemical and wireless part, the standard passive balancing CM unit up to 24 cell. You can see the rest of the details. In our master unit, we use Texas Autonomous System on Chip solution, and it consists 11 cores, normal microprocessor, and 1 GPU on top of that, and rest of the BMS is regular communication options and contactor driver circuits and etc. As a result, if I can maybe as a last wording, what we did in Albatros as an output, cloud connected BMS, system on chip solution, electrochemical impedance spectroscopy that I mentioned in detail, SOC, anode control charge, and SOH algorithms that I mentioned, and cloud architecture. All of them is tested cell level in the laboratory level right now. Hopefully next months we are going to integrate all these modules into the vehicle together with our partners, Nottingham University, and hopefully we will discuss about their vehicle results as well in the future. Thank you.
So thank you, sir, for such a broad overview of your BMS systems. Really nice. So last but not least, we'll have Cornelio from University of Aarhus, representing this time the iBatman project. So the floor is yours, Cornelio.
Great, thank you. So just a quick introduction in iBatman. We started in January. We haven't even gone through the first reporting period, so we're still, at the beginning. But in terms of introduction, like I said before, we're trying to hit a number of challenges. I mentioned that, modeling, it's a challenge because the battery pack is going to be used in different use cases. Also second life application, things like that. So more accurate modeling would be good. We're looking at different sensors, new sensors. We mentioned, some that we're developing in Helios. We're looking at other sensors as well in iBatman. In terms of connectivity, of course, we're trying to look into IoT and potentially connect the different battery systems across them, exchange data, potentially learn from that, and try to look ahead and control the battery pack a little bit more efficient. In terms of charging, fast charging, smart charging, also looking at V2X kind of applications, and of course the transfer between first life and second life, transfer of the data and the models are a challenge as well. So basically that's what we're trying to address in iBatman, a wide range of goals. Now the challenge that I have not mentioned before is that we actually have 3 use cases that we're looking for in iBatman. We have one battery pack which is produced by a company in Italy called Manifattura Automobili Torino, MAT, and I mean, you should take a look online. The cars they are producing, I mean, we can't claim that in iBatman we do the BMS for the Batmobile, but it's close to that. The cars they're making, so the fastest electric car, anyway, quite interesting. So that is one extreme use case. Maybe another use case, let's say extreme, it's in terms of the dual chemistry that we're doing in Helios. And Marble is the third one. Maybe let's say somewhere in between. So we're trying to design a BMS platform that actually fits all of them. A lot of challenges with that, but potentially if we're going to hit the goal, then that could be, let's say a bit more universal BMS platform. We have, quite a good expertise in the consortium. So you see there are a list of partners and and the expertise brought to the table. So of course, from testing, modeling, cloud, cybersecurity, of course, charging. So we have a wide range of skills that we bring to the table. And what I'm gonna go through essentially in the next slides is just a description of the work packages in terms of objectives, scope, and things like that. We don't have big results yet, but we start from a very careful requirements evaluation in terms of hardware, software, sensors, maybe looking a little bit more towards let's say Six Sigma approach kind of thing. We had the requirements exercise actually very thorough, big Excel spreadsheet, very good discussions between the experts, kind of narrowing down from there what can be done. Then work packages 3 and 4 are essentially focusing on the hardware and the software. So again, kind of integrating between the platforms, let's say from a hardware standpoint. Sensors, controls, the control units, those kind of things. And then in work package 4, we're looking a little bit more on the modeling, potentially physics-informed models, data-driven models as well. Maybe a little bit of higher fidelity, and then how do we reduce the order of these models so that we can execute them on edge, on the cloud, the data exchange between the two mediums. And then in work package 5, we're looking into the charging, cybersecurity, second life applications, those kind of things. So again, this is a pretty heavy work package from a technical standpoint as well. And then moving into testing and things like that. So it's pretty ambitious goal, but I think we can hit it. So that was a quick overview of iBatman. Thanks.
Thank you, Cornelio. We will be tuned for the next advancement. So please, speakers, if you can get here for any questions in the audience, and it's time for your questions. I probably can.
Hello, Roger speaking. Well, first, thank you for your presentations. And I would love if you can share your thoughts about this. It's like an open question. Well, 2 questions. The technical trends show that the vehicle architecture go to a zonal or domain structure architecture. What do you think that should be the role here of the BMS, specifically if we are talking of a BMS in terms of gateway that communicate with something with high computational features that can run different models of state of health, state of charge, whatever, or it should have this BMS at least some capacity to run these models. And then associated with this, how do you see the BMS in terms of the second life? If you're considering it to be in a reuse, but only in terms of vehicles, or you can reuse it in second life applications, in static applications. Thank you.
Yes, I will start with the second question. Regarding the BMS and the second life applications, usually it's very different the use in a vehicle in terms of capacity or installed energy with the one in a big battery pack for containers or etc. So at Ekerland, we are working with BMS, one BMS for electric vehicles, and then if we use the same battery for second life, we take out that BMS, we put, in that case, more simpler BMS, but then with more complex ones controlling all the BMSs or even cloud connected and these kind of things in bigger second life battery systems.
According to my knowledge or my estimation, software-defined vehicles are coming very fastly. If we have a necessary AI-based or dual computer, high complexity algorithms, we can run those algorithms in the STV side of the vehicle. BMS doesn't have to do too much computing power in that case. But on top of that, we are correct in the secondary life application where complex algorithm is not necessary. Most of them is only usable for 1C, most of or 2C maximum. They will get C. So performance requirements are very low. In my opinion, with also battery passport, cloud connection, and the secondary life option should be will be mandatory. Because of that, even though in the passenger cars especially, if there's some high algorithms run there in the secondary application, that won't be necessary. That is my summary, what can I say?
So thinking, in my opinion, this, as you said, this part is very closely related with the application that you will purpose at the end of this BMS. So it will determine absolutely the necessity, the requirements, and the necessities of enabling this structure. In my opinion, it will be as open as possible, and as such as we do in Marvel, having a very flexible system that allows through this gateway that we provide between the embedded side and the cloud-based side, the interoperability and the configuration of the system. So in this case, we keep the low computational requirements very in a lower sense in the lower part, in the embedded part, and we make it configurable and very expandable to every use case that you can think of. That's the cool part. And thinking and what this highlights is that the necessity of establishing and focusing on the improvement on this gateway, because it's the key to enable the better efficiency in the first life, and also to every other use case that we can think in posterior lives.
Well, maybe just 2 words from a Helio standpoint. Well, looking at the business case, it seems that support for ancillary services and things like that might be better than price arbitrage or time arbitrage kind of thing, right? And so in that case, a hybrid battery pack might be better positioned for that kind of application. And so BMS that would enable a seamless transition between first and second life could be valuable. From an EMS standpoint, that transition, I mean, we haven't looked into it yet. So an EMS for second life, we'll have to see how it transitions from an EMS from a first life. But potentially, having a BMS that enables this kind of, seamless transition between the 2 applications might be valuable.
Okay, any other questions?
Thank you for your presentation. I have 2 questions. First, to my colleague, Alberto. Thanks for your great work in Helios on wireless battery management system. In terms of the reliability, how do you compare it to a wired system? Because you showed basically that the distance is quite, in terms of the distance is quite robust. But I mean, you know, when putting it maybe on a rooftop, on a bus stop, and there is a lot of EMI from consumer electronics, you know, and also, yeah, electromagnetic compatibility. How do you compare it compared to a wired solution?
Yeah, so that's why I have one of the pictures where we had the CSCs put all of them in a small rack, because we were trying to do some tests, trying to cover and see how much should I cover to lose some strength and try to get some empirical KPIs before we go to the electrical bus application, which is going to be built up. As of now, as you see the video, the point is that you are starting to retransmit. So the signal does not arrive, but the system is smart enough, say on the chip level, but it's trying to retransmit until the message arrives. And there is certain some timeout at the end of the central controller, which will tell you, okay, message is not received and shut down. Yeah, this should be, but never the case. First, you are usually having a battery pack which is in a metal housing coverage. So you are taking also benefit of the reflections that you have from the inner side of the cover. So this is in favor. And secondly, the comparing to the leading chain or the wired solution of the different concepts. So in Helios, you are saving the connectors, you are saving the around about 5 to 6 minutes of cabling the battery pack over the production line, which is tremendous amount of time when you are building in mass series. So this pros and cons. Also, is the OEM ready, available, or accepting that you get the values within 100 milliseconds? So in a bus, of course, the system can work faster, but you cannot guarantee that it's going to be faster. So then is where you have the discussion with the functional safety guys, which are telling you, no, we need the value in 10 milliseconds, 10 milliseconds. And then you're asking why? In order to react 10 milliseconds. Okay. So it means it's a kind of compromise, it's a kind of discussion of the requirements for the final OEM that the system where the system will be rolled out, and also reaction time. Because you don't react at the first failure, you react after accumulating several times a non-transmitted message. And one of the cons of the wireless is you get, as of now, we have configured now for the maximum amount of numbers, you get the first failure after 100 milliseconds, second, third, fourth failure, half a second, and then you need to react. You will need to trigger the pyro fuse, not only the background. So those are also latencies that you have within your system. So the kind of compromise you need to achieve always with your
Maybe a question to SOX estimators, because it was discussed a lot. I think all of the products are discussing data-driven SOX estimation. But from Helios' standpoint, what we tested basically was that, and basically we proved that it works for two types of cells, NMC, which is quite linear, but also LTO, which is somehow nonlinear with temperature-dependent hysteresis effects. We showed that an extended Kalman filter is just enough to assure below max 2% root mean square error, which is quite fit the requirements for maybe electric vehicle applications. But what we saw basically that these estimators will diverge over time because of the uncertainties coming from aging. So the question is, if you're going to use data to fix that, does this not increase the data requirements? To which extent the cells have to be tested to collect this data to make sure that these algorithms actually work, including in second life? Thanks.
Well, as I showed before, our approach is we are trying to work with electrochemical models to produce as much data as we can, and like that to know how much data we need. And then when we jump to a real application, because we are in the research area with these algorithms, in the industrial part, we are using, as you said, Kalman filters or standard Kalman filters. And in the things that I saw some minutes ago, we are in the very beginning phase, and we are working with these electrochemical models to know how much data we need, but we don't have a number, or we don't have a feeling if they will be, the requirements will be bigger or much bigger than the ones that we are thinking right now. Yeah. Yes, but it's a really complex model that we cannot run in a BMS. Then we are using that data to develop an algorithm, or to train, to have a first model to estimate SOX. And then with real data, we want to enhance these algorithms, and we want to make them more robust. But we don't know how much data we need for that.
Okay, thanks a lot. So, yeah, sure, we have time for.
Yeah, this is for Shireen. For your EIA system, well, first, you mentioned that it's possible to be run up to 24 cells at a time, I think.
It is working up to 24 cells because our CMU connect only 24 cells, but we can operate our CMU. If you need 40 cells, we can make it 40 cells. According to module cell number, it can be changeable.
Okay, you are performing on a specific way of doing that you are passing the perturbation signal through all the cells or individual cells. So you are kind of using a kind of active balancing
Individual
system.
cells. Individual cells.
Individual cells.
If we are going, every test I am testing only one cell, but every test I am changing the cell number. So every cell will be the same condition in that every module, but you can make it module level as well. But in that case, BIS working with the, maybe you know, it's pushing to the cell sinus wave current, and if you have to push the current with module level, you have to put some power electronic circuit over there. But if you make it cell level, you don't have to make it very big electronic circuit over there, because you with 3 ampere, 4 ampere is enough for this cell level at least.
I had also the question that if you are experiencing crosstalk effects, but as you are doing at cell level, I guess that there are no crosstalks between cells.
Come again, sorry.
Crosstalk signals between cells.
No,
Okay.
there is no. Every, for example, we imagine right now, every week, once in a time, during parking condition, it will be run. It's taking only 1 minute, and every week it will do different cell. So it will, all cells will be the same condition or same, how can I say, performance after all.
And in terms of cost, if you are industrializing this solution, is it cost benefit doing this or not?
I think honestly, the how much cost additional extra for the PCB, honestly, I don't know. But in my opinion, with this algorithm, you can reduce the maybe SOC according to your application requirement also. So it will bring most benefit in my opinion.
Okay, thank you.
Okay, so thank you for our speakers. Just then a clap. And I give the floor now to Thomas again. Thanks a lot.
So it was a pleasure to be here, and thank you that you have stayed with us for 4 hours. It was a long session, but I think it was a very interesting session. We started with the main objectives when we started the 4 projects 4 years ago: reduce the weight, the volume of the battery, higher energy density, extend the range, make the battery longer, reliable, safe. And then we go into all these details of technical innovations, cooling systems, sensors, BMS as the brain. Maybe we need to make a BMS session only the next time to allow more questions. Sorry for that. So thanks to all the speakers. Thanks to the organizers. Thanks to Giuseppe and UPC for hosting us here, our event. Thanks to everybody in the battery community. I think hopefully we meet next time at Battery Innovation Days or another event. And then wish you a nice rest of the day and evening. Thank you.